Good morning. Before we start today's session, I'd like to make a quick announcement. For people who are not staying in this hotel, please send an email to Panche so we can organize your pickup from your hotel for the transportation to airport. Okay. Maybe we do the announcement at the end of this also to make sure some people everybody will hear it. Okay, good. So this morning's session is on crystal in nature and medicine. We have heard great talks so far about crystals. So today, my co-chair, Marieh, couldn't make it due to a visa issue. That's why she delivered her talk yesterday, which was a great talk. So she and I discussed, we decided to give a very brief overview of what we think the key message we want to share with everyone here. Then we introduce individual speakers to give a brief introduction of what they do, how it's related to the talk they're going to deliver today. So one message I want to send is we've been talking about crystals. Really, we need to think about crystals as materials. Crystals are cool and useful, but they're really materials we're trying to develop. Many examples we have heard so far, but think about in everyday life, it has to do with foods we eat, in terms of the agriculture, pesticides, fertilizers, important for producing foods, and health, medicines. My background in pharmaceutical industry, doing pharmaceutical research, it's a very important part of crystal play a very important part for developing drugs. Energy, right? Talk about explosives, nuclear, and solar energies, all require the use of crystals. Even for military, and to keep the peace, you have to have a strong military. There's a cool examples of wearable sensors for soldiers. And communication, I don't need to say much about that. And environment, it has to do with everyone's life. So I guess who we are, right? We're all great scientists. I guess no one will object that we are all chemists also. But I like to humbly suggest we are also all material scientists. So our work is really geared to help develop new functional materials to serve the humankind. So in that sense, because we are material scientists, the way we think, here's what I think when I do my work, really is to follow this philosophy of material science tetrahedron. So we all do different things, but our ultimate goal is to really to develop new materials that deliver certain performance, which is beneficial to us. But performance is really determined by the property of the material we develop, and properties is determined by the structure. So in fact, the understanding of the structure, property, performance relationship is first in the area of material science. It's traditionally, people call this material science triangle, right? We dedicate a lot of effort in understanding how materials work. But on the basis of this understanding, we now have the foundation of understanding. Now we can start to use various processes, which actually is engineering, right? Now we can, in order to get certain materials with certain properties and performance, we really want to change the structure, optimize it, so that we can get the property we want, which will deliver the performance that is our ultimate goal. So therefore, in this context, a lot of us are doing organic solid-state chemistry. We do the crystal engineering, and we do control the crystallization. So everything we do really fall under this guidance of material science tetrahedron. Of course, to do our job well, we need to understand the material property. Therefore, the characterization techniques are critical. Nanoparticles we really cannot see with naked eyes without these powerful microscopes. So characterization tools analyze all of the work we do. So what are the challenges and opportunities for us? So in terms of performance, I guess it's key for us to really identify applications what are the needs we need to meet. As I mentioned earlier, the many examples, nearly all aspects of human life. In terms of properties, it ranges from molecular properties, crystal property, the bulk powder, bulk solids. Really, in terms of the length scale, it's from very, very small to very large. And also the crystal structures. We've been talking about a lot of structures, but unless we're able to determine that, we really cannot understand the structure-property relationship. But there are some challenges in terms of determining the crystal structure. We have new tools developed to help us achieve that, to solve structures. We also need to do more controlled crystallization. Therefore, by doing this, we obtain crystals with desired properties, such as high purity, controlled morphology, and crystal forms. And this can be achieved through controlled nucleation and growth. And of course, we also want to be able to have the ability to predict properties, also crystal structures and properties from the molecular structure. In this sense, the cutting-edge computational techniques like DFT-based calculation, AI will be really, really useful. We should think hard how to take advantage of those in our research. In terms of the new characterization tools, this for both computational tools and experimental. So this is a very high level things where we can think a little more, try to do new work, try to deliver those. So it's my great honor to introduce our 5 speakers this morning. All of them are among the best, if even not the best, in what they do. So first, for Robert's research, his research is really focused on many aspects, but in terms of crystallization, he uses molecular modeling to achieve a morphology prediction and try to achieve the in-process monitoring of the crystallization process and try to guide the solvent selection and use seeding to achieve the controlled crystallization. And he tried to understand how the impurities affect crystallization process and also quality of the products, such as defects, purity, morphology, and solid forms. Also, the very important work is trying to develop a digital mechanistic workflow. On one hand, in academia, you try to understand things, but how do you bridge this ready to help the industry, the end user, to benefit from it? So his work is very important in that regard. And more recently, this is also the topic of my interest, is the understanding the relationship between crystal structure and mechanical property, and he's done a lot of exciting work in that regard. Some brief examples in terms of the morphology control. He showed why impurity, in this case, is sodium thionate, affects the crystallization or morphology of sodium chloride at molecular levels through a series of experiments and modeling. And he also showed how the solvent can affect the crystal morphology using similar approaches. So he's developed this digital mechanistic workflow for predicting crystal morphology. In this case, if you just use the attachment energy-based approaches. The morphology predicted from the crystal structure is very different from the actual crystals you obtain. But if you consider the interaction between the solvent and surface and molecule, once you factor in those interactions, you're able to predict crystal morphology much closer to what you obtain experimentally. In today's talk, he will give us a lecture on about the polymorphism of ritonavir. We heard about this in day one. So ritonavir is basically it was a wake-up call to the pharmaceutical industry. So ever since that withdraw from market, the pharmaceutical industry started putting a lot of money trying to understand and control the solid forms. And Kevin will try to understand this using a number of approaches. We'll hear more about that. Brown's research is on the crystal structure determination by micro-ED. Here are some examples of the crystal structure she solved using this technique. So she has developed a lot of experience on sample preparation, data collection, and processing, particularly for small molecule pharmaceutical compounds. And she has a background in protein structure elucidation, but I guess she's better known for the solving crystal structure of small molecule by micro-ED. And then more recently, she was able to demonstrate how to determine the absolute configuration of molecules by forming salts with a chiral contact. And then she also make effort, try to expand her workflow to handle crystals to be more efficient, also to improve data quality. So we're going to hear a lot of more details from her on this regarding the background of this technique, electron crystallography, also the advantages and disadvantages of micro-ED. So once we know that, you can try to apply this in your own research. And of course, she has done a lot of structures she's going to share with us today. Uriel's research, we heard about his session summary yesterday. It was excellent, very insightful. His research really focused on the interaction between solids and liquid interface at a nanoscale. He wants to understand the assembly and aggregation in biological and biomimetic systems, trying to develop new techniques to really help to understand, to capture what's happening at the interface during the nucleation and growth process by in situ scant probe microscopy and in situ TEM. We saw this diagram yesterday. Really, this is, to me, is a roadmap. Before this, people have scattered observations on nucleation and growth, but he was able to put everything together, present a map for people to really to follow, to have a dive deeper. So this essentially says that crystallization not only by monomer by monomer addition to a nuclei, is really many pathways as possible. It depends on the thermodynamic driving force and kinetics. And one example regarding the technology, this is by AFM, is the fast force mapping. He was able to show the structure of the solution at the surface of near the surface of the solid, and he demonstrated in this system is the bromide water interface. There's 4 laterally structured water layers within a very thin layer, 1 nanometer of the surface, and the one closest to the surface with highest density for the water. And he was able to reveal a very complex relationship between site-specific chemistry and density of water and long-range particle interactions. And this work really is important in the advance towards the interpretation of 3D fast force mapping. So today he will share with us some of this FM-based work and also in situ TEM work to really to give us a chance to look into the mechanism and process of nucleation and growth. I really look forward to that. Ranchevsky's research is focused on understanding the minerals on Titan, the moon of Saturn, and with a focus on core crystal formation between the benzene and nitrile. Then he has developed a set of complementary tools to characterize organic crystals, including Raman, PDF, neutron X-ray diffraction. And of course, Titan is cool, but he's also developing understanding of pharmaceutical compounds. Here's one example. Creatine is one molecule benefit for athletes to build strength and muscles. But on the market, there are two commercial products of this molecule. One is the hydrate, monohydrate, but it has a low water solubility. As you know, when the solubility is low, the absorption is slower, it's not as effective. In order to overcome this issue, other people use the hydrochloride salt of this molecule. So it dissolves faster, but you also have the after test, the acidic test. So it's not pleasant. And also the HCl is a strong acid. It have potential damage to the dental health. So he took the approach to identify this co-crystal between creatine and citric acid. He was able to prepare co-amorphous material and figure out ways to crystallize it into co-crystal and fully characterize it. But today he's going to share with us more on his work on the Titan, the cool stuff. Recently he published work on the phase diagram of the co-crystal between benzene and acetonitrile, which this can form under the condition of Titan. He wrote a review article to basically to show there's a location of various co-crystals present on the Titan. So according to that, and his talk will be on the findings so far based on the experimental modeling of the composition and structure of the various cryo minerals on Titan. Finally, our last speaker's research, Dr. Conquerio's research is on chiral discrimination in the solid state through crystallization, preferential crystallization, for example. He's trying to understand the phase purity of organic molecules and in crystal form and phase transitions. For example, the stability of amorphous solids converting to the crystal, and it's a continuum between it's purely amorphous, purely crystalline, and everything in between, also including the inclusion impurities. Some examples from his recent work. So in this case, this compound can form the stable racemate. So separate them into pure enantiomer is a challenge. So he was able to show by identifying the suitable solvent where the racemate can only crystallize slowly. So it can slow down the kinetics. And then once you form the solution, you can dissolve the racemate in the solvent, and you can add a seed of the desired enantiomer crystal. Then this seed will induce the crystallization, the growth of this phase to achieve the separation. Another example is if you have these mixtures of two enantiomers in solution, the way to separate is actually you have crystal in there, you try to using the temperature cycles, heating and cooling. In the process, because you have two solids, right? One is R and S, but they have this somehow different dissolution kinetics. Then, during, for example, in the first step of dissolution, one enantiomer will be, form smaller crystals, They will dissolve, and when you cool it, one enantiomer becomes smaller, and then when you heat it again and cool it again, these smaller particles actually dissolves faster. This is based on the oswald's ripening, same idea. So if by doing this, the one which is has smaller and less become less and even smaller. Eventually, you can get this pure enantiomer. This is another situation without impurity, but when you add a chiral impurity to it, traditionally people believe when you add a chiral impurity, you can help with the chiral separation. But in this case, actually, adding impurity leads to slower separation. And he was able to, through a series of experiments, to show this because the impurity slowed down both the growth and secondary nucleation during the cooling process. And today's talk, he'll be talking about how to actually transfer chirality from one molecule to another through the controlled crystallization. So all this work, if you only look at by itself, it's independent and complete. But if we put them together, again, we try to put the hat on as a material scientist. We need to think about the interplay between the performance, property, structure, processing. So Ronchevsky's research is really in the structure of the crystal and property under extreme conditions, and Diorio's research focuses on the controlled crystallization, right? Nucleation and growth. This is the process and structure. And Roberts and Conqueror's research really is controlled crystallization, so it's the processing. And Brown's research is really a characterization technique. Really, hopefully, all of us can use it to advance our research. Of course, for all of us in the room, right, we're all users. Our job is to identify which performance we want to achieve, which problem we want to solve, what kind of properties we need. Therefore, we can use knowledge derived from all other people's work to really achieve the ultimate goal, developing new material with high performance. So now I'd like to invite our first speaker, Kevin Roberts from University of Leeds, to give our lecture.
Carwyn, thanks for that kind introduction. It's a great pleasure to be here at ICOS again. I was counting from the book, and this is my 7th meeting. I always learn a lot, and I hope you'll see a different perspective, perhaps as a chemical engineer with an interest in solid-state chemistry. What I'm going to talk about today is an old favorite, which is ritonavir, but underpinning that discussion, I want to talk about the revolution, if you like, in digital design and digital manufacture in the pharmaceutical industry, and why we should matter. But the case study I'm going to do is on ritonavir, and I just wanted to highlight 3 of my co-workers, Chang Wang, Ian Rossbottom, and Tom Turner, who played a big part in that. So my group focuses on, as Calvin kindly said, on the work in the pharmaceutical fine chemical sector. We particularly work in crystallization science and engineering, and we're interested in how that connects to how you formulate a product. So what I'm going to try and do is I'm going to take a few slides just to talk about what's happening in digital design and why we should care. And then I'm going to try and draw attention to the evolution of the pharmaceutical, the whole debate between the crystallography in the CCDC and the crystallography of the pharmaceutical material, and as Aurora mentioned earlier on, the development of the pharmaceutical subset within the database. Then I want to show the application of engineering crystallography. This probably comes out of the Aeroche Summer School we ran a few years ago now, where we tried to link, where we made the case that crystallography is the enabling tool of a lot of digital design, and look and how that important area impacts on the crystal chemistry of materials, and particularly making use of molecular and syntonic, intermolecular empirical force modeling, which I'll focus on, and then I'll try and demonstrate that through a case study of conformational polymorphism in the ritonavir case. And the bottom line of what we try and do is I think, as Calvin has already explained, you take a molecule, you put it through a process, you come out with a product, and at the moment we do that in a phenomenological way, lots of lab work, and we get there and it's pretty good. But we really have this gut feeling that there ought to be a better way of doing this, and that's part of the agenda. So if you look at pharmaceutical materials, we have this journey: molecule makes the crystal makes the particle. From the particle, we make a nice powder. We formulate it with other ingredients, and we come out of the product. And ideally, all these activities should be carried out in parallel: drug product design, solid form selection, particle engineering, formulation time processing. But in reality, it's a stepwise process, because with significant laboratory work, and that reflects a lack of bulk material. And one of the things you'll see in this paper is we were able to work quite a lot on ritonavir because one of the industrial companies gave us a lot of material. And that's a big factor. You know, I think you can develop materials really easy if somebody gives you a kilogram. It's very hard to do it with a few micrograms. Product attrition mitigates against doing a lot of work, because typically 90% of all drugs in development don't make it to market. This is a big factor. And also, we don't really know enough about what we're doing in engineering. So there's a lot of F words in life, particularly in research, and we know them well. And here's 5 which I think are quite important. We start with a formula, which is a molecular structure. From there, we go to the formation, crystallization, spray drying. From that produces the form, which is the crystal size, the morphology, the polymorph. And from that, the formulation, which we might do by blending, granulation, compaction, and that impacts on the functions. And that, through Calvin's concept of the material structure, tetrahedron, sort of tells you the kind of things that you want to do, how these various factors relate. Understanding the chemistry of crystal surfaces, and particularly crystal-crystal interfaces, is important in formulation. Why we need to look at the morphology of materials, because it's the surface chemistry, it's where the intermolecular interactions are broken, and those broken interactions that drive the product properties. And these interfaces are mediated by solvents, additives, crystal formation, and more importantly in formulation, the excipients and the other ingredients we put into a typical tablet. What we get out of that is this digital design concept integrates material science, structure versus property relationships, chemical engineering, processing, product performance, quality assessment. And that synergy and that holistic is the driver, in my view, for the development in the next generation of healthcare materials, and one that this conference particularly has a massive contribution to make. So I want to see us move towards an industrial need, because by benefiting industry and society, we benefit mankind. So if you want to go back, it's always good to go back and look. And if you go back to 1947, you get the invention of the transistor, for which Barden, Shockley and Brattain got the Nobel Prize. In silicon, there has been 75 years of research on a small molecule, if you want to look at it that way, a semiconductor material. Outcome, incredible performance. A lot of the things that are driving us have come from this 1947 invention. Though before that, everything was valves. Pharma R&D has to deal, though, with not just silicon. It has to deal with a multitude of drug compounds, each potentially with many different forms. It's not at all uncommon in a process development to have 50 solid forms to deal with, to have to do a selection, to need to know their physical properties. But if you look at what the pressures in our process R&D, we get about 6 weeks to do it, not 75 years. Industry needs in the pharmaceutical sector is smarter, quicker, more agile to meet global needs, and particularly this drive towards personalized medicine and zero carbon and more recently pandemics. We need to be pretty nippy. So if you look at that innovation space, the innovation in the pharmaceutical R&D is largely lagged behind. I mean, we do not make prototype aeroplanes anymore and test them on the ground with a hammer. We digitally design them to work, and they do, largely. Similarly with automotive products. They're not made the way they were 50 years ago, and certainly microelectronics isn't. And there's a lot of new science. Advanced analytics, we've seen big data, AIs, genomic mapping, personalized medicines are redefining the medicines portfolio. And we see this enormous seismic move away from the manufacture of a small number of high-tonnage, blockbuster, one-size-all-fits medications. If you take breast cancer, you can't have a single treatment of that. It's a biological predisposition issue, and there are at least 20 different variants of it. One medication doesn't do it. So where we're going to is supplying a multitude of targeted APIs produced at a much smaller scale and formulated over a wider range of dosage forms. Typically, drugs are formulated at 3 dosage forms, small, medium, and large. And the reason for that is the burden to get through regulatory authority is quite high, and we want to reduce that. So we'd ideally like a dozen dosage forms and a dozen medicines for every one. This is the key opportunity to exploit digital design for making precision medicines. 6 sigma quality, so narrow crystal size distribution, low variability, high purity, high stability. Why should drugs have a short shelf life? Well, this is a reflection on the manufacturer. A narrow therapeutic profile means you need less drug, and therefore much greater efficacy and less risk. And if you look at this shadow graph, classic diagram on that, you can see where the cost is at the bottom, but you can see where the influence is. And design, it has a massive shadow, cast a massive shadow, get the design right, it has a huge impact here, and we sometimes focus too much on the cost basis. What comes out of that is this realization that we not only want to digitalize manufacture, but we want to be able to do de novo design. That's our ambition. That's our challenge to the academic community. Not to say this is difficult. Of course it's difficult. But that's why we're academics. We do difficult things. And if you look at the things that academics have done, we've done this over a long period. So the growing importance of de novo digital design tools to rapidly, sustainably develop future drug products. Okay, so that's my heads up as to that. And I want to today talk briefly about 2 outcomes of this ADOPT project, Advanced Digital Design of Pharmaceutical Therapeutics. And basically, it seeks to connect all the process up, from crystallization of a material to how you get the size right, to how you blend it with the excipients, to how you then manufacture it in terms of a tablet form, and you give it to the patient. And you get this high-level workflow, and then underneath each of these are all the things you need to know. So it's a route map for how you would develop something, and particularly we go from this route map to workflows for the individual area. So we take away some of the green fingers in research and say, look, actually, this is not as difficult as we're making out. Focus today is not on all this. The DOT project had some 20 postdocs working on different areas. I'm just going to focus on one case study within this sector. And particularly, this whole concept of the holistic high-level triage workflow underpinned with a structure of properties, processes, outcomes, and see how they come together. So when we look at molecules like this, we look at the academic space, and I'm a bigger culprit as anybody else. We have the academic space of looking at simple molecules like ibuprofen, and then the industrial colleagues looking at much more complicated things, and ritonavir is a good example. And we look at that and we say, oh, for PhD work, that's too complicated for my students. And we tend to do model work on aspirin, paracetamol, and simple organic molecules like that. And there is a question to ask, why? And as someone once said to me quite roughly at a conference, if people like you don't do difficult problems, where are we going to go? And I think there's an interesting point there. So what can we learn from looking at these two molecular structures of these two compounds? Which one might be polymorphic and why? Well, it's obvious. Ibuprofen doesn't really have more than one polymorph, and ritonavir has quite a lot. I want to say a little bit about another outcome, not from our group, of the DOT project, which was the development of the pharmaceutical subset, and Aurora touched on that in her wonderful lecture at the beginning of the conference. And this basically delved into the CSD, which had about 1 million structures, and said, well, let's just corral all the drug-like compounds. And you've got this data here. I'll show a few of these. So this is the difference between acceptors and donors. And you can see that how this is translating along here. So here, if you look at this dotted line, I've just dotted around AstraZeneca's compounds, you can see they've got a lot more acceptors and a lot less donors. And that's just one trend you see. So the subset is great as a research tool because it highlights more complexity in drug molecules when compared to small molecule model systems. And it's the need for the academic community to look at complicated systems. For example, the protein crystallization community don't have a problem working on proteins. They say, this is my research. But strangely, in the solid-state chemistry ones, we tend to steer a little bit away from that. Two other trends that come out in molecular weight. You can see as you go for the year approvals of drugs, the molecular weight is consistently going up. The number of rotatable bonds going up. So what do you think comes out of that? Well, obviously, the more rotatable bonds, the more likely for conformation of polymorphs, and the molecular weight goes up. It's very, very important. It tells you that dispersive interactions will be a lot more important. So if you're in a small molecule, you can accept that maybe hydrogen bonds and electrostatics play a big role. But once you get to big molecules, you know that dispersive van der Waals interactions are really a big determinant factor. Year by year, the molecular weight, the number of asymmetric unit components, and the number of rotatable bonds, and the delta bond acceptors minus donors is all increasing. It tells you the direction in healthcare and the molecules we need to be capable of modeling. Okay, so now we go back to ritonavir. So it's an apt time to talk about ritonavir because the original really good source paper by Bauer et al. Is about 2001, and we wrote our paper thinking, oh, that's convenient. 20 years since Bauer's paper, why don't we use that as a pitch point? So the story, and I think it's fairly well known, is that the ritonavir is the API, norvir is the product, and the product was capsules of ritonavir in ethanol, mostly ethanol, and it has low solubility, aqueous solubility, so it was made in the semi-solid capsules. They did a solid form selection, they found the stable polymorph, or that's what they thought, and they tested it, as you do, by doing making lots of lots and doing lots and lots of testing. And basically, around 1998, there was a big problem. They were threatened as a result of a much new and much less soluble form of ritonavir. It's important to note that ritonavir is an important drug today, not only as an antiviral for the dreadful AIDS epidemic of the 90s, but more recently in combination medicines in the COVID-19, and that's formed quite an important medical treatment for COVID. So this was the original press release that came out. We have encountered an undesirable formation of ritonavir crystalline form 2 that affects how they dissolve. In form 1, all the strong hydrogen bond donors and acceptors have been satisfied and are strong. Aha. So, question, is this true? And I think you see the answer is not quite. It's not quite true, and that is the problem. Since the strength and completeness of hydrogen bonding has been attained, the maximum possible in form 1, that is, it is not thought possible that another undisclosed polymorph of ritonavir would exist with equivalent or lower solubility of form 1. Well, that proved to be the case. Later, they did lots of screening and they found lots of polymorphs. And that follows the Walter-Macron logic that the number of polymorphs is directly proportional to the amount of time and money you spend on it. So you have to be careful about making bold statements. The lessons learned, I think, is that we need a detailed understanding of the molecular and crystal chemistry of all materials in order to control polymorphic behavior. This is the original paper. I won't dwell on it, but I do think it's a really good source paper, and I use it in teaching. It's very, very good, and it makes you think about how things were 20-odd years ago. And these are some of the pictures. You know, what they found, they did slurry experiments, and they added the opposite form, make a form 1 solution, make a form 2 solution, then you add the opposite seeds in, it always ended up with form 2. Distinct powder patterns. And broadly speaking, the morphologies were elongated, they were plate-like in form 1 and needle-like in form 2, and we'll go back to that right at the end. But basically, you always get form 2. So this is the synthonic engineering workflow: work on the molecular properties, work on the solid state properties, and then look how those solid state properties are terminated by the surface features. It's probably useful, if you're not familiar, just the kind of engineering approach we've taken to intermolecular interactions. Basically, if you think about it, the synthesis of molecules involves making and breaking of covalent bonds. And the synthesis of materials is pretty similar, really. It's someone humorously called Chapter 2 of the book. The bonds are intermolecular interactions, intermolecular synthons, and when those take place within a material, we call them intrinsic materials. So you take this lovely co-crystal of carbamazepine nicotinamide, we can see all these synthonic interactions between the molecules. And it's worth remembering that the interactions are interactions between all the atoms in the interacting molecules. Our eyes go on the hydrogen bond because we say the hydrogen bond is the strongest, but it's only the strongest per atom. It's not the strongest necessarily per molecule. And that's a huge factor when the molecular weight goes up. When these are at the interfaces of the material, we call them extrinsic synthons, and the extrinsic synthons are important. Synthons, of course, from an engineering perspective, are vectors. They have both magnitude and direction that is driven by the crystallography, which is why the crystallography is important. And you can predict them with molecular and crystallographic modeling, and you can manipulate them through subtle changes in both the molecular chemistry and the surface chemistry of the material. Extrinsic synthons direct the physical chemistry properties of the material. They drive nucleation, crystal growth, polymorphic form purity. They drive the toxicity, the degradability of the material. It's the functional groups that are exposed on the surfaces that basically dictate shelf life. And they're also particularly important in understanding how the API and the excipients you put into a tableted formulation, for example, how they their adhesion, cohesion properties and formulatability, do they flow or do they compact, are all driven by those surface properties. What comes out of that, heads up I guess, is that molecular scale synthetic modeling enables the understanding of bulk and surface properties of crystals for use in formulated product design. It's useful. So let's go back to the pharmaceutical subset, and these are just, this is some of the data from the subset in a number of areas, number of donors, number of acceptors, number of aromatic rings, rotatable bonds, molecular weight, and C log P, which is basically the hydrophilic, hydrophobic basis. And you can see where ritonavir sits, always at the edge. This is something one would think about. So compared to the CSD drug subset, ritonavir is even then atypical of many aspects of existing crystal structures and having a particularly significantly higher molecular weight. And if you apply Lipinski's rule of 5, which is a very nice rule of thumb for development, it basically says an oral drug should have no more than one violation of the following criteria. No more than 5 hydrogen bond donors, no more than 10 acceptors, a molecular mass less than 500 Daltons, and an octanol water partition coefficient not exceeding 5. And you can see that mostly it doesn't pass that. And that tells you that is the genre of medicines coming through. And then when we look at the biological classification system, are basically permeability, high permeability versus solubility, we sit right over here in class 4. So a clear lack of alignment with Lipinski's criteria is consistent with a class 4 classification, low solubility and low permeability, but nonetheless a very good active ingredient. And it's our challenge to develop a method to deal with it. You can learn a lot from the crystal structures of ritonavir, and here is just the solved structures from Bauer's paper plus a little bit of work by ourselves. And we can note, what can we see from this? And I always think, first of all, from the posters also, what's the structure, what's the space group, how big is the lattice, how big is Z? And let's have a look at some of those. First thing you notice about this is that form 2, the molecular conformation, is more compact. You can see from the molecular volume is smaller, the molecular surface area is smaller. Just more compact. It's more stable, so you can see this from the melting point and the enthalpies of fusion. And you see immediately, once you know the enthalpy of fusion, this will be less soluble. So it's fairly obvious stuff. Form 1 is a simpler structure and easier to assemble. Now, that's an interesting thing. So when you see something, and we were discussing that at posters in a simple space group like P2, P21, you can see that there's only one symmetry operator, and the self-assembly process is going to be a bit easier. And then you've got the stable structure as P21 to 1 to 1, so you've got 4 symmetry operators to get that intermolecular interactions right. Also, form 1 is a polar space group, it's P21. So, and in general, structures don't like polar structures. It's not a thing that nature likes. So you can I would get, if I see a polar space group, I think, that'd be interesting. I don't know why, but it just tickles something in the back of my mind. But form 1 is more closely packed. See, higher density. This kind of spoils the Ramberger rules. This is why they're rules and not laws. So here in this case, the packing coefficient is higher, the void space is less, and the density is higher for the metastable phase. That does happen. Close packed structures are not necessarily the most stable. That is the kind of early take-home message. Would they have known at the time? I think they should, really, broadly speaking. And this concept, there is 2 lattices going on. There's the lattice of the van der Waals interactions, and which is isotropic, undirectional, and there's a lattice of the hydrogen bonds, which are fiercely directional. And they are kind of fighting it out, and you'll see how that pins in. So this is a very nice diagram drawn by Tom Turner in the paper. I think it's in the supplementary materials, but basically lays it out in 2 dimensions. And there is quite a lot. It's a bit geeky, but the key thing about the 2 polymorphs, which was pointed out by Bauer, is that a lot of it forms around the conformations around two groups, the N-methylurea and the carbamate conformation. And in form 1, it's cis and trans, and in form 2, it's trans and cis. And the other thing you notice that when you do a charge calculation, some of the form 1 structure is more polar. We'll come to later on. So these red boxes show the atoms that undergo a reasonable amount of change from the conformation. And the conformation's quite radical in this molecule. So conformations within the two polymorphic structure differ significantly, notably around those groups. As I say, form 1 is cis-trans, form 2 is trans-cis. And that could suggest that there are other polymorphs, particularly cis-cis and trans-trans, still to find, those interested in structure predictions for brutal molecules. The different conformations of form 1 and 2 give rise to different molecular polarizabilities, with form 2 being slightly more polar. And then when we look at the conformations, finding the conformational minimum for a molecule as big as that, no small task. I don't know what the most stable molecule is. That's been studied, but not described terribly well. But if you just calculate the single point energies of the two conformers, you realize that form 2 has a strain energy of around 8 kilocalories per mole. So to get it into form 2, the molecule has to distort away from where it ideally wants to be. So the conformation of deformation penalty for form 2 molecular structure is consistent with its observation of a slow nucleation process. And the whole thing about ritonavir is it's not magical, it's just the form 2 primary nucleation is very slow indeed. And there are plenty of very slow primary nucleation processes. But once you form it, secondary nucleation takes over and you can routinely get it. And you can get an idea of still staying with the molecular agenda from the conformations here in space Philly models, and you can see that a key thing is this hydroxyl group in the middle. And in form 1, the hydroxyl is only a hydrogen bond donor, because the oxygen is not so accessible to be an acceptor. And that's because of the conformation of the molecule. So the hydroxyl group is somewhat buried in the form 1 structure, impeding its capability. So the molecule is so big, even though it's got a good set of donors and acceptors, it's difficult to align those. It's a bit like aligning a spacecraft for docking. If you look at form 2, it's a lot more available. It's a lot more available as a structure, and you now in the form 2 conformation, you can see that you can get to both the hydroxyl oxygen and the hydroxyl hydrogen, and that was the missing link. They thought they had satisfied all the hydrogen bond, but they didn't realize the importance of the hydroxyl oxygen as a hydrogen bond acceptor. Arguably, they should. I would think even 20 years ago. So another thing you can do when you do that is you can start to look at how that molecular structure assembles by doing lattice energy calculations as a function of the limiting radius of your sphere. And you can see that at form 1, this is, if you like, the lattice energy. This is the lattice energy form 2, lattice energy form 1. This is obviously more stable when you get there, but the form 1 gets there first. Yeah, it gets there first. So form 1 gets to its lattice energy at a much smaller radius. That is tied in with nucleation theory. So you know intuitively that if you want to get a small radius, you need a high supersaturation. And so it tells you if you wanted to get a stable form, you would have to crystallize it very slowly. And this is something in crystallization science is obvious. It's something you would know you would have to do it. If you want to get the stable, you crash something out of solution, you'll always get the metastable form. And so you see. So the lattice energy convergence with size explains why it did not appear in the early stage development, because it's very soluble. If you ever dissolve this thing in ethanol, you can't get it out of solution. It's like a soup. And so you naturally tend to drown it out with an anti-solvent, but then you've got to be really careful to keep the solubility, the supersaturation down. What this comes out is the lattice energy of form 1 converges at smaller cluster size compared to form 2. And this, along with Form 2's high deformation energy, explains its lower nucleation rate. It's just a slow nucleating system. When it gets there, it's there with you, and you, as they found out to their cost, you can't get a shot of it. I won't dwell on this, but it's worthwhile saying we find it very useful to go through the intermolecular interactions and classify them in a geeky manner, shall I say, for both, this is Form 1, this is Form 2, to see how the molecules assemble. And for example, you can do quite elegant calculations with Cosmo-RS and things like that, where you can see the propensity of these intermolecular interactions in solution. But what comes out of it is, if you look at the Form 1 synthon pair, you'll see it's got a couple of hydrogen bond interactions. And if you look at Form 2, it's just got a single one. But each of those, as we'll see in a minute, are comprised of, well, this is comprised of 4 hydrogen bonds. This is 3 hydrogen bonds and 1 hydrogen bond. So there's still 4 hydrogen bonds in both polymorphs, but they're distributed in a different way. But you can see how the change in conformation changes. You can see this interleaving structure for this B1 synthon that you can't get in the same manner for the other one. So understanding that is useful. But the vast majority after these top hydrogen bonds are van der Waals interactions. Later you see that impacts on the morphology. And then you see this a little bit better now. These are the 2 hydrogen bonds. This is Form 1, so this is the A1 and the B1 structures. And you can see there are 3 hydrogen bonds here and the 4th there. And in Form 2, these are the 4. This is what they didn't spot, that the hydroxyl should be an acceptable, an acceptor, hydrogen acceptor. Now this is even more geeky, and I apologize, but it is in the paper. What I've done here is I've color-coded all the donors, so blue and blue match. So you can see how the crystal chemistry is changing. So there are 4 hydrogen bond donors in the structure, the amide, the N-methyl urea, the carbamate, and the hydroxyl. And you can see how they change. And the key one is the one associated with the B1 synthon, where you can see the acceptor is the thiazole. So this is another thing you might have noticed in development. So you had this crystal structure when you developed the material. You might have thought to yourself, OHN, isn't there a better acceptor than a nitrogen? Maybe. And later you'll see that same one down here is, where is it? Has found a better pair. So you basically got an OHN and an OHO, and the OHO is always likely to be a stronger interaction. So and the other thing you see is the hydrogen bond distances are much longer in Form 1 than in Form 2. So the hydrogen bonds are shorter and stronger in Form 2. In Form 1, there are these 3 NHOs and 1 OHN synthons. In Form 2, there are 3 NHOs and 1 OHO. So and because of the conformations, they're able to get closer. Because they get closer, they get stronger. Whilst the hydrogen bonds strongly contribute to the energetics of the structures for both forms, achievement of an optimal close packing is impeded for Form 2. In order to make those hydrogen bonds, it can't close pack, and it doesn't. So what comes out of that is that the hydroxyl group is only a hydrogen bond donor in Form 1, but a donor and acceptable in Form 2. Then we can have a look at it. We can, with some degree of geekiness, we can just keep on going, and we can start to look at how those forces break down. And we can see the important thing here, as I mentioned earlier on, how important van der Waals interactions. For both of those structures, they contribute the bulk of the lattice energy contribution. And it's higher in Form 1 because it's more close packed than Form 2. And again, coming out with the density being higher in Form 1. Solid-state interactions, both of them dominated by van der Waals interactions. Form 1 is denser, less voided, more close packed, but less stable structure than Form 2, but with a greater van der Waals contribution to lattice energy. Form 2 is more stable than Form 1 with a greater electrostatic and hydrogen bond contribution to the lattice energy, but with hydrogen bonds preventing optimal close packing. Summarizing that, different conformations change the balance between space-filling van der Waals interactions, which dominate form 1, and directed hydrogen bond interactions that dominate in form 2. Another geeky piece of synthonic analysis, which is worthwhile doing, is to start to look at the two conformations and then grab us. This one here, we've segmented into 4 sections of such a large molecule with the idea of saying, well, how do they contribute to the overall lattice energy sum? And you can see this group here, the gamma group, is quite important. So we can have a look at that in the next slide. So doing that intra-atomic interaction analysis, so you calculate the intermolecular interaction, and then you try and work out which of the interatomic interactions is most important. And here you can see this again in 2-dimensional with the 4 sectors split. And you can see that if we take this gamma group, we can see how important this central hydroxyl group is, which is much stronger in the form 2 structure than in the form 1 structure. And so it tells us, what are the kingmakers in the functional, not only in the molecules, but what are the kingmakers or queenmakers in the functional groups between the intermolecular interactions. So from this we get quite a lot of data, and a lot of the proposition in writing this paper, which also has a lot of supplementary material, was to make the point to the industry that this is the kind of information that should be provided in drug submission. So you want to demonstrate you really are on top of the crystal chemistry of your drug. And here I just want to show you how this pans out from the synthons of the 2 forms to the extrinsic synthons. So now we look at those synthons and we then cut them with a habit plane and go which ones have been cut. And the important things you see here is these important hydrogen bond synthons. See all these row of zeros? I won't go into it too much. See these row of zeros? They only contribute to the capping faces of the crystal. So you can kind of know just from this analysis that this will be a needle-shaped crystal, and the needle axis will be dominated with hydrogen bond interactions, and the sides of the needle action will be van der Waals interaction. That's very important when you're choosing a solvent. Sorry, I've highlighted those. So hydrogen bonds only contribute to the capping faces, and that explains the needle-like morphologies for both forms. And here, this is a classic analysis you'll see in a lot of our papers. We take the morphology of the material and we go, what is the surface chemistry of those faces? Because the point is this community is very strong on molecular chemistry, and I think unless you address what is the surface chemistry of the material, you can't hope to understand how that might transform. We remember yesterday's paper, the lovely paper on the copper sulfate pentahydrate and forming the adduct. Lovely work. You need to know what is the surface chemistry. Why is it driving? And in the origins of this group actually was in a lot of topochemistry, a lot of reactions, solid state chemistry. How do these things happen? They inevitably happen at interfaces where intermolecular interactions are fractured. It's kind of the same as semiconductor science, but with molecules. It's just the same science. So here, basically they're elongated molecules, that's fine. Form A is a bit more tabular, which is what you saw, and form 2 is a bit more elongated. So they both give you elongated molecules, that's because there's strong hydrogen bonds along. Each habit expresses quite different surface chemistry, suggesting that the 2 forms might interact differently during development. So, when you know the surface chemistry and you're going to put this in a formulation, say with a solvent like in a capsule, or you might put it with a alpha lactose in a tablet, you kind of want to know what the surfaces are going to see, and you get, as you've seen from co-crystal forming, you get reactions, and that's something worth knowing. Each crystal habit face exposes different surface chemistry and crystal planes. And finally, you can calculate the surface energy. So I just want to show you that you can treat this. It's a bit more geeky chemical engineering, but you can treat this as a mass balance. So from the predicted morphology, you can calculate this relative surface area, and then you can do this. You can calculate a weighted surface area. So you calculate the surface energies of all the individual faces, and then you weight them by their multiplicity and their area, and you basically get a surface energy of the particle. And getting the surface energy of the particle gives an important parameter for how it might process. Okay, so does, maybe right at the end, a couple of slides, just on the experiments. Now, it's called a disappearing polymorph, but actually you can, I have to say, you can crystallize it quite easily. So it's most, this is Chang Wang's time in these. I said, well, could you please study the crystallization of form 2? I said, you can't get form 1, it's disappeared. He said, oh, I made it in the lab yesterday, I think it's all. And basically, I said, well, how did you do that? He said, well, it's common sense, isn't it? It's just Ostwald's rule. If you want to get the metastable form, just call it fast. And so he called it as fast as the crystallizer would go. And form 2, you do it really slowly. And he said, no, no problem getting crystals. So these aren't really disappeared. I think we don't want to use, I sometimes think that's a bit misused. It's fairly lab work, fairly routine lab work to get that, and someone skilled in the art should know how to do that. So, but that is with this prerequisite of starting with a Form 2 material. Of course, there was no Form 2 20 years ago. And this is what the crystals look like. Now, there was having a look at some of these. So basically, 3 solvents. This is good standard solvent selection if you're doing it. Choose a protic solvent, a polar protic, polar aprotic, and an apolar solvent, and because that will enable you to see. Now, if you remember, the sides of the crystals are hydrophobic, the capping of the face is hydrophilic, so it's no surprise that if you crystallize it in toluene, for example, in both forms, they expand out. The toluene glues like hell to the sides of the crystal. It hates the ends of the crystal because they're hydrophilic, and the crystals shoot out as long needles, and that effect is less. If you take a protic solvent, you know the protic solvent will love the ends of the crystal because that's where all the hydrogen bond donors and acceptors are. And lo and behold, you get quite chunky crystals. So the basic principles of molecular recognitions enable you to get the crystals that you want. The other thing, if you're a bit geeky like me, I've always been interested in polar crystals. You can see the effect of a P21 space group. You get these sort of pyramidic type crystals pointed at one end due to that polar nature. Small crystal size and polar morphology for form 1. Look, these are 2 microns, this is 100 microns. So in order to get this, you basically reflect the fact that you need a high supersaturation to get form 1, and that pushes the nucleation rate up, and that pushes the crystal size down. High supersaturation, small cluster size is needed to make form 1, which result in small crystals. Okay, let's close off. So what have I attempted to do? I've tried to give some context to current research in engineering crystallography within this evolving digital design space. This is basically what I wanted to do. I wanted to highlight the importance of de novo design set within a holistic system-based R&D. So solid-state chemistry have a massive impact to make on that. And it's important that they engage with some of the future challenges, in my view. I've tried to discover some recent and current research from the ADOPT project. This is a massive project. I mean, we had an open day on this and there were a whole day of presentations. But I wanted to highlight, not my work at all, this is CCD's development of the pharmaceutical subset, because I want to recommend it to you as a very useful resource for fundamental work. There's a couple of posters from more recent project, P1 and P2. And I want to highlight really just a case study work into trying understanding the structural origins of conformational polymorphs in ritonavir. The work, just a glimpse of the current work on digital design and for our future personalized healthcare. There is a lot to do, and I just want to say again, I think this community's got a lot to offer, and it will be pivotal. So acknowledge basically the ADOPT project with a lot of companies. Synthonic engineering work has been, since the first version of Habit was released in 1991, we've had continuous financial support. I can't grumble at all as an academic. Grateful to the Chinese Scholarship Council for Chang Wang's and AbbVie who provided the material. So just some overarching message, not the conclusion, sort of the more general thing to think about. It's important to understand these causal links between molecular, crystal, and formulated particle properties and the processing parameters that connect them. And that is through the material science tetrahedron of Calvin as energetically promoted. Then assess the impact of all these connectivities on drug product performance. And that's vital for the development of our future healthcare provision. And this lovely graphic from Bob Doherty, here's a molecule, space filling, becoming the crystal, coming a formulated product, and then dissolving in the patient's stomach. Thank you for having me. Thank you for giving me the opportunity to talk to you today. Thank you for this wonderful conference in a wonderful place and a great bunch of people. Thank you.
Thank you, Kevin, for a wonderful lecture. Maybe we'll take one question. Yes, that's.
A very short question about the Lipinski rule. The numbers are quite random, increments of 5. Is that a little bit, too much of a random number to be called a rule?
Yeah, I think you're right. So I put Lipinski's rule of 5 up because it is a rule of thumb the industry uses quite a lot. And I suppose in a certain way I was having a bit of a tease. I've never been, some of you know me well, I've never been a great believer in rules and laws because that's usually a good excuse to show that they don't work. And I think that Lipinski's rule of 5 works for small molecule crystallography quite well. But it is a bit fanciful, as you rightly say, choosing numbers that are nicely divided by 5. I agree.
Thanks, Kevin. Yeah. I'm sure there are more questions. Please catch Kevin during the coffee break or during on the boat, maybe. I invite our second speaker, Jessica Brown from Nano Imaging Services.
Tested it earlier and it works, so.
Yes, we did. While waiting, maybe I can take a survey. Who have used micro-ED in your research? 1, 2, 3 over there. Okay, not many of them. Okay, so hopefully after the lecture today, the rest of you, learn more about this technique and can use it more in our research. I personally feel it's a very powerful technique. You're gonna give it some time. Going to become a mainstream technology for structure elucidation. Yeah. Apology for the glitch, technical glitch. Yeah.
I guess I can Maybe I can
Come here, yeah.
Yeah, okay. I can at least start with my intro slides are a little not as interesting, but just kind of introducing who I am. So I'm Jessica Bruin, and I'm from a company called Nanoimaging Services, and we're a contract research organization offering transmission electron microscopy services to the pharmaceutical and biotech industry. And so we own our own fleet of microscopes, all from Thermo Fisher. We were founded in 2007 and installed our first Glacios microscope in 2018. That's the one we used for micro-ED collection, and it's looking like maybe this is gonna work. Okay. Yeah. So the company is kind of divided into 3 different service groups. So we do a bit of single particle cryo-EM with our microscopes, so looking at protein structures and drugs bound to those. We also do a lot of just imaging with the electron microscopes, taking pictures of vaccine samples or lipid nanoparticles. And then I run the group that works on structure determination for small molecules using micro-ED.
Yeah, from my experience, Jessica is, maybe one of the most active person in trying to promote this technology. She has, gained a lot of experience. It's a good opportunity for us to hear her experience today, if we can make this work. Yeah.
Just one tray with USB.
Okay. Oh yeah, sure. That should work. Yeah. Seems it's coming off. Yep.
Thank you. Okay, that's fine. All right, thank you. No, thank you for finally getting that to work. All right. Fantastic. Here we go. So I'll just kind of skip through my intro slides, which I've already introduced the company. I guess I didn't mention that we're located, we have 2 sites, one in San Diego, California, that's where I'm located. We also have a site in Boston, in the Boston area in Massachusetts. And so this is the fleet of all the microscopes that we own. And I've circled in pink the 3 microscopes that we use for micro-ED data collection. These are equipped with SATA-D cameras, which are specially designed to collect high-quality diffraction data. So as I said, we've been working in the micro-ED field since 2019. That was when we upgraded our camera to this SATA-D camera. And since then, we've looked at over 150 different samples sent in to us by people from all over pharma and other industry and some academic groups. And internally, we've phased and refined over 60 structures. A lot of the data that we collect is processed by our clients, and so I'm hopeful that a lot of this other data that we've collected has resulted in other structures that I'm just not aware of. So, all right. So now I'll move to a bit of an introduction to the field of micro-ED. So micro-ED stands for microcrystal electron diffraction. This is a technique in the 3D electron diffraction umbrella field. There's a nice review article that I recommend looking at by Mauro Gammi and his co-authors published in 2019, describing this nanocrystal revolution. So the big breakthrough here is that we are using electrons as our radiation source instead of X-rays. And this allows us to look at much, much smaller crystals, orders of magnitude smaller than those required for X-ray crystallography. We're able to do this because electrons interact much more strongly with matter and produce scattering from even the tiniest crystals. And so this technique has been applied to a wide variety of materials, things from inorganic crystals, zeolites, to metal organic frameworks, to classic small molecules, especially pharmaceutical compounds, peptides, and even proteins. All right. So I have just a very brief timeline of the field, and there's lots missing here, obviously. So it's been long known that electrons interact strongly with matter and produce diffraction, but it was really in the 1990s when work from the Dorset and Hofmüller groups and other coworkers really started looking at collecting zone axis diffraction patterns from crystalline materials, from three-dimensional crystals, and using these patterns and imaging to determine structures of organic and inorganic materials. But in these early days of the field, this technique was incredibly challenging, and there were only a handful of people working in this field. There were a lot of difficulties with multiple scattering events, also known as dynamical scattering, challenges merging data, and just a lot of difficulties in the data collection. It was very laborious to align the crystals along these zone axes to get useful data. So a big breakthrough occurred in 2007 by Uti Kolb, who will be speaking on Friday at this conference. I'm really looking forward to her talk. So she proposed kind of a new method of collecting data and moving away from only collecting data on these zone axes and just collecting data at other angles. And so she developed a technique called automated diffraction tomography, which she'll speak about. It's a slightly different way of collecting data compared to micro-ED, but it's has a lot of really useful applications, and again, we'll hear more about that on Friday. So I think for everyone in the audience, one of the most exciting moments in the field was these back-to-back publications in 2018, one from Tim Groon's group and one from Timur Gonen's group, both showing that we could apply a slightly different data collection method. This is a continuous rotation of the crystal using electron diffraction to collect high-quality data and quickly get structures of organic small molecules. And so the Gonen group prefers to call this technique micro-ED. Others in the field might refer to it more broadly as continuous rotation electron diffraction, or just use the 3D ED term. So apologies for the confusion in the field, but we're all somewhat talking about the same thing. So here's a little look at the kind of the growth of the field. This is something people are always interested in, how many structures are being solved. And so you can see, in the early days, it was a handful of structures being deposited in the CCDC each year, and now things have grown quite a lot. And I assure you that these numbers are an undercount. It's very difficult to actually find all of the electron diffraction data. I mean, the CCDC has over 1 million structures, and we're talking about a handful of them. And it's a bit hard to find them all, but this is my best attempt at finding the ones I can. And then I'd also point out that I'd estimate, just from informal discussions with other people working in the field, I think there's probably an additional over 300 structures that have been solved for pharmaceutical companies that probably will never end up in these data banks because pharma companies don't like to put their structures out there unless the drug's on the market. And so, I think what we see in the data bank is just the tip of the iceberg. And I want to thank Lee Daniels, who I was emailing with back and forth yesterday to help me get some of this data. All right, so a little bit about how the technique works. So it's very analogous to other diffraction experiments that you're used to. You have a radiation source, in our case it's electrons, and crystals, which in our case we have placed on a flat TEM grid surface, transmission electron grid. And then when we expose these crystals to the beam, we'll get a diffraction pattern like you're used to seeing. And when we couple this with continuous rotation of the stage, we can collect data in a manner that's analogous to the way that most single crystal X-ray data is collected. Which moves me to kind of a comparison of these two orthogonal techniques. So single crystal X-ray diffraction is by far the most commonly used technique to solve crystal structures. It produces really high quality data, has very quick turnaround times. It's just a very well-established field with decades of work and instrumentation. You can pretty much, with modern collection techniques, you can generally get absolute configuration information, and it's just a great overall technique. The only downside really is, growing large enough crystals to perform your single crystal X-ray experiments. And so for some compounds, this can be quite challenging, and some crystal forms may never be able to form a crystal large enough for X-ray. So I've listed some size limitations here for X-ray. I'm sure that people will argue about these exact numbers, but there is a bottom size limit for these crystals, and the numbers I have here are generally for the smallest dimension of the crystal. So there is room for accessing structures from smaller crystals. So microED, on the other hand, this is our big advantage, is that we can actually work with these smaller crystals. The ideal size of our crystals is kind of less than a micron, maybe more than 200 nanometers in thickness, and then the other dimensions of the crystal can be larger for this technique. And generally, I kind of prefer crystals that are a bit larger in the other dimensions, just that I have more copies of the unit cell and more intensity data. So this allows a lot of groups to skip crystallization trials, optimization, and just move forward with their crystalline powder material, which is a great advantage. Another advantage of microED is that we can process our data in X-ray programs, such as Apex and Chrysalis Pro that you're used to working with. This is one advantage over ADT, which Uti will talk about on Friday. Absolute configuration is now possible. I'll talk about that a bit later. And then the big cons are, of course, that it's an emerging technology. Things are moving quickly in the field. There are higher costs due to very expensive equipment. Our microscope and camera runs on the range of about $2 million US, so it's a lot of money for this equipment, and the data processing is quite a bit more challenging. So my bottom line opinion here is that if you have suitably large single crystals, just go ahead and do X-ray if you have access. I think that's probably the best first choice, but if obtaining a large single crystal is too time-consuming, requires too much material, maybe your group lacks expertise in growing crystals, or you just couldn't get one after a significant amount of time, I think that's where microED is there to help and still get structures. All right. So, as I said, at Nanoimaging Services, we routinely determine structures for people working in pharma and other industries, and I'll share a bit about how our pipeline works. So we start with sample submission, and generally we ask for about 1 milligram of material. We can certainly work with less, but it's always easier to have a little bit more to work with. And then we also have been asking that our clients confirm that their sample is crystalline first by doing just a quick powder diffraction scan of their bulk material, or they can perform that with us, and we'll just take a small amount of that 1 milligram and collect a spectra just to make sure that the sample's crystalline and we're not wasting microscope time. Next, we'll prepare a grid. The grid preparation is pretty straightforward. Typically, our first pass attempt at this would just be to put the powder onto a glass slide, press our little 2 millimeter TM grid against it, and the crystals will just stick, the same way dust sticks to cars. And we'll tap off the excess and just put that into our microscope and start collecting data. So in the microscope, we will use imaging mode to take real images of the crystals and kind of look around for the best ones to target. We might look at diffraction preview before setting up collection, and then we can start collecting data from multiple different particles or different targets on a single particle. In some cases, we won't find good diffracting crystals. We might go back and prep a second grid using a different method, such as resuspending the crystals in something they don't dissolve in, and then drying that suspension on the grid. We maybe will need to heat the grid a little to remove volatile contaminants like water. We have a lot of little tricks to kind of get the best out of a sample that we're given. All right, so next we will do data reduction and phasing. So this is a little bit more complicated than a single crystal X-ray experiment, primarily because we generally combine data from multiple crystals. So, in an easy case, we'll get a structure pretty quickly, maybe an hour or so. More difficult cases can be more involved and take, a day or two of data processing to actually phase the data. And I'll emphasize it's an iterative process. We often go back and try different data reduction strategies. If the first thing we try we can't solve, we'll just keep trying things. And then if that fails, we'll sometimes just go back and collect even more data. The particles are really variable in their diffraction quality, and maybe we'll find a slightly better crystal that can help us get us over the edge of being able to phase the data. Just very briefly show this slide to show, so we're using our own data collection software that was written by this woman, Anqi Chang, who's part of the company, part an academic. And if you want to know more about this method, you're welcome to check out our paper. But basically, data collection works by us identifying crystals in imaging mode images from the microscope, selecting them for data collection, and then when we collect a data set, we continuously rotate the stage from -60 to +60. This is roughly the limitation of the stage in our microscope, and we'll collect continuous rotation, electron diffraction data in rolling shutter mode. And we're able to queue up data, automated data collection from a number of crystals and collect hundreds of data sets overnight without user intervention, which is a nice advantage of our system. It's also open source, which is nice. All right, so as I mentioned, data processing is more challenging, again, because of needing to combine crystals. There's also dynamical effects, optical imperfections in your microscope that can lead to problems. I've written a tutorial for processing data in a program called Dials. That's the one I prefer to use. There's lots of other options. I encourage you to check out that tutorial if you're interested. And I'm also co-organizing a micro-LED workshop at the ACA meeting in Portland just in a couple weeks. So there's still time to sign up, but you do need to show up in person for this workshop if you're wanting to learn more about data processing. All right. So I have just a couple of little notes about the technique. So as I mentioned, absolute configuration is possible by micro-LED. So this is our ability to define the chirality of all the chiral centers in a chiral molecule. Racemates are very easy to determine by micro-LED, but for enantiomer chiral compounds, you have kind of two options for determining your absolute configuration. You can either look at relative configuration relative to a chiral center of known chirality. And so Bo Wang and I from Biogen published a paper about this just a little bit ago. And then there's also dynamical refinement, which has been pioneered by Lukáš Palatnis in the Czech Republic. And this is another method of getting absolute configuration that requires no prior information. And I'm happy to tell anyone more about that. Just grab me at a coffee break. All right. Another exciting thing about a micro-LED structure is this wonderful relationship between micro-LED and powder diffraction data. So you can take a micro-LED structure, so this is progesterone, a structure that we solved, and you can take these coordinates and plug it into mercury and generate a predicted powder diffraction pattern. Which is great, but it's even better when you combine it with a measured powder diffraction pattern and compare these two spectra and kind of understand the relationship between the structure you solved and your bulk material. Do they line up? Is there another phase in there? That sort of stuff. I also just have a small comment on the accuracy of these structures. This is a comment that the field gets a lot, and there was a paper by Brigaku in 2021 where they looked at a couple of early micro-LED structures and kind of concluded that these are pretty poor quality models compared to X-ray. And so I looked at one structure that they looked at in their paper. So this is a paracetamol structure that we solved and deposited in the CCDC. And at least our structure, at least this one that I looked at, is looking a bit closer to the X-ray structures and doing a bit better than these really early day micro-LED structures that they were comparing to. And so I just encourage you to give the field a chance. I think our structures are quite nice. And if you want more examples, so in the paper with Biogen, here's an overlay of an X-ray structure that Bo determined and a micro-AD structure I determined, and the RMSD between these two structures they're nearly identical. It's very hard to see in this image, but the only real difference you'll see in the models is that the thermal ellipsoids from the micro-AD structure are quite a bit larger, but the atomic positions are quite accurate. Another great paper just came out from Merck, using some of our data in that paper, kind of comparing micro-AD, CSP coupled with powder diffraction, and single crystal. They looked at 3 structures in that paper, and the RMSD between our micro-AD structures and their single crystal are very, very low. And then this is another paper that I've published with kind of aggregate data from a bunch of structures we've solved and kind of showing what sorts of R values and things you should be expecting out of a good quality micro-AD structure. All right, with that, I will move on to some case studies and just some exciting examples of the application of this technique. So the first case study is just a very obvious application, which is just, we have a sample, we couldn't get a single crystal X-ray structure, and we'd like to know the structure. So let's try micro-AD. So this is a compound that we selected. It's called tinipicide. It's a cancer drug. It was FDA approved in 1992, but there was no single crystal X-ray structure available in any database that I could find, which led us to kind of speculate that there might have been difficulties in obtaining a large crystal, and maybe this is why no one has reported a crystal structure of this compound. So as you can see, the molecular weight is a little bit high. We're, again, violating Lipinski's rule of 5 here. And there are 6 rotatable bonds. It's not quite as complex as some of the molecules we've seen, but up there. So we put this in, we purchased this compound from just a vendor and put the direct powder from the vendor onto a grid. We found these rather ugly looking particles. They're not the, the surfaces are not the cleanest, but we were able to get diffraction data from these and determine a micro-AD structure from this sample. And so this is what I would say a more lower quality structure. The resolution of these crystals is about 1.2 angstroms. Despite that, we were still able to phase this data, get a pretty reasonable structure, and assign all of the non-hydrogen atoms pretty confidently. So we were pretty happy with this. It's deposited. Welcome to check it out. Another nice thing that I can share with this compound is that we also measured the bulk powder diffraction pattern from this sample, which is the dark blue line here, and compared it with our micro-AD generated powder diffraction, simulated powder diffraction. And you can see that these two spectra, they line up quite well. There's a little bit of shifting in the peaks of the two patterns, which we speculate is probably mostly due to thermal effects. So we do our micro-AD measurements at 80 Kelvin, and the powder diffraction was measured at 100 Kelvin, and so there will be unit cell expansion contraction with temperature changes, which is probably where the differences come from. But from this comparison, we can conclude that there was no phase change from the bulk material to the micro-AD structure. So exposing this to vacuum in our microscope, the temperature, and any radiation damage did not. It doesn't seem to have changed the structure, which is great. And then we also see that there aren't too many extra little peaks in there. So we think that there's only one phase in this this bulk powder, and then we solved it. So that's what we conclude. All right, so my second case study, so this was a company that was, they were scaling up to the kilogram scale of production for their API molecule. They had a six-step reaction, and unfortunately, step 5, once they started scaling up, they started producing this unknown byproduct that they didn't want, and they didn't know what it was. So of course, they, ran mass spec on this compound. They could tell that it was a little bit higher molecular weight than what they were expecting out of step 5. They looked at NMR and kind of tried to piece together what this compound might be. They went through quite a lot of steps to try to determine this structure. They tried single crystal X-ray diffraction. They couldn't get big enough crystals. They did a lot of sophisticated NMR experiments. They sent it to a CRO to perform some fancy high-temp NMR experiments, and none of this was successful. They just couldn't quite figure out what had gone on here. So they sent it to us, and thankfully for us, it was a really ideal sample for micro-ED. They had these beautiful little needle crystals here that would be too small for X-ray, but are great for us. They produce just really high quality diffraction. We got pretty lucky on that front. And we were able to determine a structure, which I can't share with you because this is pharma, but anyways, we were able to show them what it was, and now it is a known byproduct, which is great. So one other thing in looking at the structure that we were able to see is that there was this addition of a formal group to the compound and some unusual ring rearrangements that had occurred. And so from this, they were able to realize why this product was occurring. So there was some formaldehyde in step 2 that must have been hanging around in their reaction and was reacting with the product from step 5 and producing this unwanted byproduct. So then they could go back and try to design a better strategy for production that removed this formaldehyde and prevented this from happening. Another great thing from this structure was that they were able to take our structure and simulate the powder diffraction pattern. And now they were able to use this as a kind of a fingerprint to, every time they run step 5, they can collect a bulk powder diffraction and look for trace amounts of this unwanted impurity and kind of look for any amount of it, and they can really identify if they're having a problem again. So this was a great success. All right. Now we'll move on to my last example. This is a rather big project. So this was a company doing solid formulation screening. So they're just trying to find the best solid form for drug delivery. And they had generated 5 different forms with different, some are free base, some are with some acids. And they actually, it was interesting, this is a group that came to us as, micro-ED was their first choice, mostly because they didn't want to have to wait for growing large enough crystals for single crystal X-ray diffraction. So this was a nice case there. And yeah, so we took this on and we put these into the microscope and saw what we got. So the first, we solved a structure of form 3. This was a pretty easy, straightforward. It turned out it was a hydrated HCl salt, so that was kind of interesting. Form 2 turned out to also be a hydrated HCl salt, but there was more water content. Then we looked at the free base, found it was a partial hydrate, solved that structure. And then on to form 1. So this was a very challenging one. So they had good powder diffraction data showing that the bulk material was crystalline. When we put it in the microscope, we found just a lot of these large particles that appeared to maybe be agglomerates of much smaller crystals. This is showing almost no diffraction from this particle. We hunted around and we reached out to them. We said, this sample is not going to work. We're sorry. So they went back. They hired 2 different CROs to produce some crystalline forms and sent them back to us. And one of those 2 CROs was able to get a slightly better sample. So in here, we found a handful of these thin plates that were isolated from the other particles. We were able to get some reasonable diffraction and actually solve this structure. But yeah, it was interesting for us to see that these 2 different CROs, only one of them could get a good enough sample for this. So this was just a very hard project all around. All right, so in looking at this structure, one of the big questions we had was, and one question that you always have in pharma is this a salt crystal or a co-crystal? Has proton transfer occurred between this weak organic acid that they were using and their active pharmaceutical ingredient, their API? And thankfully, micro-ED is very well suited to address this problem. So typically, when approaching a problem like this, we will do a pretty conservative refinement of their structure. So we'll model the whole rest of the molecule, but we'll leave the proton in question alone and not model it until the very, very end. And so this is what we did in this case, and we can see quite clearly that there is a little Q peak here in the structure that we solved, indicating that there might be a proton here near oxygen 4. And we also looked at the density maps. So the 2FO minus FC map showed a little point pointing in that direction near the oxygen. The nitrogen here was pretty spherical, I guess. And then the difference map showed quite a nice peak for this proton. Another feature you'll notice maybe is the bond lengths here. So The carbon-oxygen bond here is about 1.18 angstroms, kind of short. This carbon-oxygen bond is 1.29, much longer, indicating that this is probably a single bond, and this is probably a double bond. And then the Q peak here is very close to this oxygen, 1.16 angstroms. That's about where a hydrogen should be, and it's super far away from that nitrogen. So of course, we modeled all the possible locations for this, this hydrogen and looked at the R factors. And in this case, modeling the model of no proton transfers, so this is an OH and this is an NH2, produced the best R factors, and we concluded that this was, in fact, a co-crystal and not a salt crystal. All right, so back to our list of forms. We've now solved this, this form, which was a co-crystal. Onto form 5. So form 5 was a bit interesting as well, in that we actually solved 2 structures from their one sample. So we were able to determine another partial hydrate. This is a different polymorph of form 4. And then we also solved the structure of an anhydrous form. So this is a bit puzzling, what's going on here. And we went and looked at a comparison with the bulk powder diffraction. And we found that the partial hydrate structure matches quite well with their powder diffraction, but the anhydrous crystal doesn't really match the powder diffraction. We didn't really see the peaks lining up there. Here's just for your information, the composition that we saw by micro-ED. So in the microscope, these crystals diffracted at very high resolution, so we only collected 21 data sets. 5 of those 21s were the partial hydrate, 16 were the anhydrous. So by micro-ED, you might conclude that this is mostly the anhydrous form, which it possibly is, but I add in this caveat that micro-ED is not a bulk measurement. We are only measuring data from a handful of crystals out of the thousands on this grid. Also, the preparation of that grid, some particles stick to the grid material better than others, and so there can be bias in that. And then also large particles tend to fall off the grid. So there's definitely bias, and in other experiments we've shown that there is bias in what we see in the microscope and what's really in the bulk. So it's always nice to have that measured powder diffraction to go back to kind of say what was in the bulk powder. And so from this we concluded that if there were these anhydrous crystals in the bulk material, they were probably a very small fraction, and we're just seeing a small fraction that happened to stick to the grid better for whatever reason. Or it's also always possible that the TM vacuum dehydrated these crystals and induced the formation of these crystals. So, it's a bit of a mystery, but this is the best we can do. And in the end, it's a pretty good deal. They sent us 5 samples, and we got them 6 structures, so including a new form, so that was exciting. All right, I will just toss out some closing remarks and just say that micro-ED, we're able to unlock structures from crystals orders of magnitude too small for single crystal X-ray diffraction. This can avoid laborious crystallization, screening, and optimization. And in many cases, this is the only or the best option for challenging samples. Absolute configuration is definitely possible from these data. There's a lot of power in comparing a micro-ED structure and the bulk powder measurement, and also with good instrumentation and data handling procedures and good crystals, these should all result in highly accurate results. With that, I'll thank my coworkers at Nanoimaging Services, a handful of my collaborators, and many community members who I've had good conversations with, and especially our clients and some funding that we've gotten from the NIH. Thanks.
Thank you, Jessica, for the nice presentation. Now we open for questions. Okay, we have one there. Yeah.
Thank you very much, Jessica. Simon Parsons, Edinburgh. Can you say something about beam damage and how you avoid it? I think you routinely work at 80K. But how often do you find beam damage, and what do you do about the data collection conditions to minimize it?
This is an excellent question. Yes, so most of these materials are radiation sensitive, and so we minimize our exposure as much as possible. I'm collecting data for only about 30 seconds on the lowest setting the microscope can do, which helps, certainly. It does decrease my intensity values that I'm measuring to measure at such a low dose, but it's worth it for radiation-sensitive materials. I'll also say that I didn't get to go in the details of data processing, but this figure here is a look at scaling results from 4 different crystals combined, and the orange color, I guess, is your R merge value and frame number. And so you can see that in crystal 2, there's a big spike in R merge versus frame number towards the end of collection, probably indicative of beam damage. And so often what we'll do in the data processing is we collect all of the data because it's worth it, what's 10 more seconds in the microscope. And then we computationally will trim out those radiation damaged frames when we're combining the data from multiple crystals. And so hopefully we'll have hit some region of reciprocal space and with less damage. But yeah, that's kind of how we avoid it.
Okay, thank you. When you say the lowest setting, this is a power setting, essentially, the intensity of the incident beam.
Yeah, it's a combination of gun lens, spot size, and the intensity. I mean, we need to be in parallel illumination, so we're a little limited there. But yeah, and I have many data sets deposited in Zenodo, and there's a 3D community there, and all of my data collection parameters are carefully written out there, so you're welcome to look and see what we're using. Obviously, it was optimized for my microscope, which has a FEG is our source, which is, I guess you're using a tech dice, so it should also be a FEG, but there may be differences between each microscope about what settings are best.
Is there wavelength dependence?
Yes, yes, there certainly is. So we're collecting with a 200 keV microscope, and off the top of my head, I struggle to remember the name of the author, but there have been papers written about this, and I think some of the big disadvantages of collecting at 300 keV are that your lower resolution intensities are, or your phase information from these low resolution intensities are not as great at 300 keV, but there's much better experts in the field than I on this topic. Now, I'll send papers later. You're welcome. Certainly.
Can I make a comment on beam damage? Diffraction is very insensitive to damage usually, because you see only the ordered stuff. So one question here is actually if there is beam-induced crystallization. And it will be interesting to compare the first diffraction that you get, and after you do all the tilt, go back and see the first compared to the last one to see if there is something. Okay, yeah.
Certainly. Yeah. No, that's a great, and I imagine too, once you have a final model, you could take wedges of data from early in collection and later and refine them against your structure and see if you see differences, certainly.
I forgot the second question. You mentioned a continuous rotation?
Yes.
So how many snapshots you make in such?
So I'm optimizing for beam damage and the limitations of my equipment. So I collect typically about 130 images in 30 seconds. So my oscillation per frame is 0.89 degrees per frame and 222 milliseconds per image. But these numbers came from kind of optimization of what is best for my camera, mostly.
And there is any correction, like software correction afterwards for the shift during the, or it's just not important? I don't know.
Yeah, so hopefully the scaling step can help with some of these. I think some of the important things are what volume of crystal was in the beam at a certain point. That correlates directly to how bright the spots are, and so I think mostly it corrects for that. But it will, in theory, scaling should also correct for other, if the height changes, the detector distance, and that'll also be corrected in the cell refinement stage, kind of correcting for these things.
Thanks.
Mm-hmm.
We'll take one last question.
Thank you. Thanks very much for that really nice talk. I'm Helena Shepherd from the University of Kent. Can you say something about the spatial resolution that you can achieve with this technique? So can you perhaps map domains or that sort of thing in the kind of XY plane?
I didn't put it in the slide deck, but I've looked at kind of the typical resolution limit of the crystals that we've looked at, and they tend to be kind of in the 1.1 angstrom range, but I don't think that's what you're asking about. I think you're...
So if you've got a crystal, could you scan across it? And if so, how small a slice could you scan across?
Yeah, we'll often collect multiple data sets from one crystal just to save time, less movement of the microscope. And yeah, I haven't looked at can we see subtle differences, like for example, on the tip of a growing edge of a crystal, and is that a little different? I don't know, possibly.
Thank you.
Mm-hmm.
Excellent talk. One question, you compare the accuracy of the data between single crystal diffraction and your data, but how about powder X-ray diffraction? Because people can solve and refine structures, and that's a fair comparison to make, right?
Yeah, no, certainly. And I would just point you to, so this paper by Justin Newman at Merck, they have 3 powder diffraction structures solved by CSP methods, and the RMSDs are very, very similar between their structures, the micro-ED, and single crystal X-ray. So yeah, it's a good example.
Okay, yeah, we'll have the coffee break now. And before we go, just one reminder: if you are staying in a hotel other than this one, please email Penchair so he can arrange the transportation for you. So, thank you. Yeah, we come back at 11. Yeah. Thank you. Yeah.
I couldn't fight it. I'd hope to see my face, and that to be reminded that for me it isn't over. Never mind, I'll find someone like you. I wish nothing but the best for you too. Don't forget me, I beg. I'll remember you said sometimes it lasts in love, but sometimes it hurts instead. Nothing compares, no worries or cares, regrets and mistakes, their memories made. Who could have known how bittersweet this could taste? Never mind, I'll find someone like you. I wish nothing but the best for you too. Don't forget me, I beg. I'll remember you said sometimes it lasts in love, but sometimes it hurts instead. Sometimes it lasts in love, but sometimes it hurts instead. Easy, ready, willing, all the time. Where does it stop? Where do you tell me to draw the line? You've got the body, now you want my soul. Don't even think about it, say no go. Well, I'll do anything that you want me to do, baby. Well, I'll do anything that you want me to do, baby. But I can go for that, no can do. I can go for that, no can do. But I can go for that, no can do. But I can go for that, no can do. I can go for being twice as nice. I can go for just repeating the same old lines. Use the body, now you want my soul. Oh, forget about it, say no go. Well, I'll do anything that you want me to do, baby. Well, I'll do anything that you want me to do, baby. But I can go for that, no can do. I can go for that, no can do. I can go for that, no can do. But I can go for that, no can do. clock on the wall has just told you your hour is gone. And you know those that God loves die young. There is never forever, only the moment, the moment. There is never forever, only the moment. You're thinking too much about who will think badly of you. You throw away chances, let love pass you by. There is never forever, only the moment, only the moment. There is never forever, only the moment. Da-dum, da-da-da-dum, da-dum, da-dum, da-da-da-dum. There is never forever, only the moment, There is never forever, only the moment. With guilt in your shoulder and fear in your heart. The devil by angels belittled by fools. There is never forever, only the moment, There is never forever, only the moment. Don't be afraid of the dark. generations through into the boundary of each married man. The street the sitcoms calling and negativity lands. Cold, cold heart done by you. Some things look better, babe, just passing through. And it's no sacrifice, just a simple word. It's towards living into separate worlds. But it's no sacrifice, no sacrifice. It's no sacrifice at all. Mutual misunderstanding after the fact. Sensitivity pulls a prison in the final act. We lose direction, no sun unturned, no tears to damn you. When jealousy burns, cold, cold heart done by you. Some things look better, babe, just passing through. And it's no sacrifice, just a simple word. It's two hearts living into separate worlds. But it's no sacrifice, no sacrifice. It's no sacrifice at all. Cold, cold heart done by you. Some things look better, babe, just passing through. And it's no sacrifice, just a simple word. It's towards living into separate worlds. But it's no sacrifice, no sacrifice. It's no sacrifice at all. No sacrifice at all. No sacrifice at all. It was good for me, it was good for you. Nothing either of can say or do can change the way you feel tonight. Sometimes love just leaves aside. Just one thing before you go. Just one thing that you got to know. No one will ever touch me that way, the way that you did that very first day. And I tried so hard to rise above. The years go by, there's always someone new to try and help me forget about you. Time and again, it does me no good. Love never feels the way that it should. I love you then, I guess I love you forever. And even though I know we could never stay together, think about it, how could it been if we could just start all over again? And I'll never be the same without you here. I'll live alone, hide myself behind my tears. No, I'll never be the same without your love. I live alone, tried so hard to rise above. It was good for me, it was good for you.
Well, welcome back. We had a good, wonderful two talks earlier. So the first talk after coffee break is by Jim Diorio from University of Washington. Jim, take it away.
Okay, now it's hot. Okay. All right, I'm sure you can all hear me. So first I want to congratulate Ponce and the other organizing team, the rest of the organizing team for doing such a great job in putting this together. Fabulous program and an amazing spot. And I thank them for giving me the opportunity to be part of it. I'm going to talk about interfacial controls on crystallization in biomolecular and biomimetic systems. Let me first give you some motivation for this. Protein assembly into crystalline structures fills dual roles in biology, and that process depends on control over interfacial interactions. I have two examples here that represent these dual roles. The first one is the assembly creates functional materials on its own. So the example on the left here is so-called carboxysome. It's an organelle that is one of many similar types of organelles that are found in bacteria. And you can see that it consists of, well, it's a sort of a vesicle, right? It's a geometric shaped vesicle. But it's, the vesicle shell is made of proteins, and each of these units is a hexamer of individual identical monomers. Now, of course, the primary structure dictates the folding and what groups are going to interact with one another, but it's the interaction between these that leads to the quaternary structure, the quaternary architecture, and that occurs through the process of self-assembly, both to make the hexamers and then to make the larger structure. Now, if it were only hexamers, this would just be a flat sheet, but biology is clever, and you can see that there are some number of pentamers thrown in, and those cause the thing to fold and ends up making this closed vesicle. So it's this sort of hierarchical structure that ends up being functional, but it's the self-assembly process that needs to be controlled in order to produce it. Now, the reason it's functional is because the assembly creates these pores where you have these peptide loops that stick into this region, and that controls what goes in and can come out of this vesicle. In this case, it's bicarbonate ions, and they get turned into fixed carbon by enzymes inside like Ribisco. And so these kinds of objects, which are in bacteria all over the planet, are an important part of the carbon cycle. On the right-hand side is the other example of, the other role of protein assembly, which is not to create structures that are on their own functional, but they end up being scaffolds for the production of hard tissues, which then, of course, give structural support, cutting and grinding tools, etc. This is the one that's most important to all of us because it enables us to stand up and walk around. It's collagen. Individual collagen monomers, so-called topocollagen molecules, 3 of them assemble to make this trimeric unit, and those trimers then assemble into a pseudohexagonal fiber where the end of one collagen molecule comes some space before the start of another, and so it creates regions that are called overlap and gap zones. And mineral precursors can diffuse, these then assemble into these quasi-hexagonal packed structures. So if we looked at a cross-section, you'd see a hexagonal array. And then you can see in this TM micrograph from Nico Sommerdijk's group where the mineral components diffuse in through these certain bands. The banding structure here is because the electron density is different in different places where the amino acid residues overlap, and so this is a very characteristic pattern of the organized collagen. The dark lines the vertical dark lines are actually the platelets of hydroxyapatite, calcium phosphate, that form in this matrix. So this highly organized matrix produces a highly organized, very hard material that has great mechanical properties, despite the fact that collagen on its own is quite a weak and not very useful material. And the mineral platelets are little nanoplatelets that have very little strength on their own. All right. So the question that we have tried to address is, well, how do natural systems achieve order? How do they direct mineralization? And then secondly, can we design synthetic systems that carry out these kinds of roles for our own purposes, for technological reasons? For example, well, there's nothing magical about this. I mean, it's polymer, and it assembles, and then it directs mineralization. So can we make some that direct the formation of N-type and P-type semiconductors and make 3-dimensional arrays of microelectronic materials? Well, it's a dream, but there you go as one example of what you might think about doing. All right, so I'm going to give you first I'm going to start with a natural example, and this is, okay, how does it work? So I want to talk about tooth enamel. Tooth enamel is a natural example of a highly organized mineral tissue formed within a protein scaffold. It's got a lot of parts to it. I want to talk about the outermost part, enamel. It's the hardest tissue in the human body, and it's a highly organized structure. This happens to be from a mouse, but human teeth look like this as well. What you see is this woven structure, and the bundles that are woven here are bundles of individual nanorods, or nanowires, I suppose you might call them, of single crystal hydroxyapatite. Now, what's interesting is that there's almost no protein in this, so it's 96% mineral and 2% protein. But it starts out being all protein, and the protein gets digested in the process. So we actually don't know what the scaffold looks like. We only know what the product looks like. So one of the big mysteries in biomineralization that many people have been trying to solve is, how does tooth form? Well, in about a decade ago, a group at UC San Francisco, Stefan Hablitz's group, discovered that, or realized that amelogenin, the protein scaffold that gets digested, has an amyloid region, and that if you bring it to a somewhat low pH, not too low, maybe 4 or 5, that it self-assembles into a cross-beta sheet structure typical of amyloid fibrils. Of course, we think of amyloids as being part of disease, but amyloid is actually a functional structure as well. In this case, it forms 2 leaves. The hydrophobic sides are against one another, and the top and the bottom are identical. They're the beta sheets of the sides of 2 beta sheets that are crossed over one another. And here's a TEM image of these amyloid fibrils that form from amelogenin. So we asked the question, well, okay, we know you can make these fibers, but do we actually know that they nucleate calcium phosphate? And if they do, how do they do it? So we set out to look at this with Stefan's group, my student Susra Akkaneni, who just finished his PhD this year. Investigated 5 sequences. All of them contain the amyloid region, the 14p2. 14 stands for the number of amino acid residues. We made other sequences from this. For example, we phosphorylated the serine site here. That is the case in the full-length protein. That site is phosphorylated. We added on the C-terminus, which is known to bind to hydroxyapatite. And we also used the full-length protein, although it's not the phosphorylated version of the full-length protein. So what did we find? Well, first of all, so these assemble in solution into the cross beta sheet structure. All of them do. But that doesn't do us much good for studying nucleation because there is no technique for looking at nuclei on individual proteins in solution. However, AFM can do this quite effectively, and what we found is that these will assemble into the beta sheet ribbons on graphite. Now, it's not cross beta sheet, it's only 1/2 because now the hydrophobic side doesn't need the other beta sheet to get away from water. It puts that hydrophobic side down on graphite. But the side that mineralizes, that's exposed in the cross beta sheet, is the thing that's exposed to the solution. And all of these sequences form these beta sheet ribbons, these amyloid ribbons. I'm not going to talk much about this. I mean, this is just showing you that they're all there. You can see from this image, though, this very similar pattern to what you see here, and that's the beta sheet ribbon that you're looking at. All right, so what did we find? So we did nucleation experiments. These are now, these surfaces are fully covered in these ribbons. And I'm showing you two, one that's not phosphorylated and one that is. It's just the 14p2, the amyloid region. And you can see that they both cause nucleation, but at very dramatically different rates. So the phosphorylation has a big impact on nucleation. And eventually you can start to see the outlining of the ribbons as more and more nuclei form. So Susrit did this for all of the sequences at multiple concentrations, supersaturations, and you can see how they mineralize at different rates. And eventually, these last images are actually late in the experiment when you can observe the phase transition from this initial phase, which turns out to be amorphous calcium phosphate, to the hydroxyapatite phase. And I should have mentioned that it's largely believed and been, there's good evidence for the fact that in the tooth, the first phase to form is the amorphous phase, and it later transforms to the crystalline phase. I also should say that, you know, this ribbon motif provides a natural motif for creating, you know, nanowire-shaped mineral, and so it's kind of exciting to think that, oh, it self-assembles into these ribbons. They would naturally drive the formation of ribbons of hydroxyapatite, which they do in our experiments. Okay, so what do we do with this data? So I want to take you back to nucleation. I talked about this yesterday. So I showed you the Gibbs model for nucleation in bulk solution. And the point I want to make here is we're looking at heterogeneous nucleation, but the framework for understanding it is identical. You form a mineral particle. It has a bulk term to the free energy, which can only happen if it goes downhill and the chemical potential is negative, change is negative. But now there are three interfaces. There's an interface between the particle and the solution, and that's the one that we had in the case of a particle in bulk solution. There's also a new interface between the particle you're forming and the substrate. And then there's an interface that got covered up. And you have to take that into account too, right? Because if you look at the change in free energy, you've hidden that piece of the surface, and so you've changed the free energy just for that reason. So the net interfacial free energy is actually contains all three of these terms. And this term, alpha heterogeneous, is going to be smaller than alpha liquid crystal as long as this term in the brackets is less than 1. And that just simply says that the interfacial energy between the crystal and the substrate is less than the interfacial energy between the liquid and the solid, right? And liquid and the solution. I mean, the liquid and the substrate, right? That's why it's going to form on the surface, because it's going to lower the free energy, because that's a lower interface, and lower energy interface than the one that was there. All right, so the rate equation looks identical to what it was before. The form of the free energy barrier is the same as it was before. If we take the log of this expression, we now find that the log of the rate is proportional to 1 over the supersaturation squared. The slope gives us this interfacial free energy. It's this composite term, but that's okay. And the intercept gives us this prefactor, which tells us about the kinetics of ion binding and desolvation, okay? So if we know what our supersaturation is, and we do this experiment as a function of supersaturation, we can measure the rates, we can get these numbers. And so that's what we did. So first of all, here's a plot of the number of nuclei per area versus time. And this, of course, I should say that, you know, the rate goes up for a while, and then it becomes 0 because you get the surface all covered. We only take the data from the region where the rate is increasing. And wherever it's increasing linearly, you know that you're in an area where nuclei are not affecting one another. They're all independent events. Now you can take the slope of this, and that now gives you the rate, the number per area per time. You can see that this is for all 5 of these sequences, and we did this as a function of a number of supersaturations. Now, we also can measure the rate of growth of the particles, and we can do that as a function of the ion activity product in the experiment. And those will extrapolate back to 0, which is the activity product at equilibrium, right? So if we want to know the supersaturation, we need to know both the actual activity product, which we set, but we also need to know the equilibrium activity product. And so we get it experimentally by finding out where, this is a very standard way of figuring out where equilibrium is. So now with that information, we have supersaturation, and now we can plot the log of the rate, which we get from these slopes, versus 1 over sigma squared, which we get from the known activity product and the equilibrium point. And from these slopes, we can pull out the interfacial free energy, and from the intercepts, we can pull out this kinetic prefactor. So what do we find? Well, first of all, if we just look at the absolute rates and pick a place in supersaturation space where we've done experiments on other proteins, we find out that the phosphorylated amylogen and nanoribbons are the most potent amorphous calcium phosphate nucleators ever reported. So this is another form of amylogen and nanospheres, which for more than a decade were thought to be the important motif in enamel and nucleation of hydroxyapatite to form enamel. This is amelogenin nanospheres with enamelin added in at a ratio of 50 amelogenin to 1 enamelin, which gives you the highest nucleation rate. This is collagen. And you can see that if you look at the non-phosphorylated versions of our proteins, our peptides, they're better than the amelogenin nanospheres, but not as good as with the addition of enamelin or collagen. But when you look at the phosphorylated ones, they're much stronger nucleators. So that's conclusion number 1. Conclusion number 2 is if we look at the interfacial free energy, and here we've normalized it to the value of the 14p2 sequence, which is just the amyloid fragment without phosphorylation. So that lies here at 1. What you see is that there's really not a lot of variation, but in addition to that, the interfacial free energies for the phosphorylated versions are actually higher than they are for the non-phosphorylated. They're all low. They're all very low compared to bulk solutions. So they all promote nucleation. But the phosphorylated versions are better, and not because the interfacial free energy is lower. If anything, it's worse. But when we look at the prefactor, what we find is that the prefactor scales with the net charge of the peptide or the protein. And because the phosphorylation sites are negatively charged sites, they lie at the top of this line, okay? And so it's the kinetic prefactor that's really driving the high nucleation rates on the phosphorylated nanoribbons. And so what's that do to? So we did molecular dynamics simulations with Henrik Hein's group at UC Colorado. Sam Hoff, a student of his, did this work. I think he's now at the Max Planck. I better be careful about that. That may not be true. He's somewhere in Europe. Sorry. I can't remember where he went. And it turns out that these phosphors, so these things assemble into the beta sheet. And it turns out that when you look at where these phosphorylation sites are, they're really well positioned to match the structure of this calcium triphosphate unit I mentioned yesterday that is the starting unit for making amorphous calcium phosphate. And so we end up with this really nice model where, you know, we have a low interfacial energy interface, a low energy interface, but we have ion binding sites that sort of template the multi-ion units that start the amorphous phase. The consequence is that if you just try to do it in the bulk and make HAP directly, you've got a big barrier. It's easier to make ACP first, but if you do it on these nanoribbons, the barrier to making the ACP is even lower. Okay. All right, so we also set out to see whether or not we could design proteins that can do this kind of thing. And this is work with a wonderful collaborator, David Baker from University of Washington. Anybody who's in the protein design world knows David. He's the inventor of Rosetta and one of the individuals in AlphaFold, responsible for AlphaFold. These are, a former student of his, now a postdoc there, and another student, Fatima Davia, and Harley Piles, who are doing the design work. And so here's an example of what we did. We're using a motif that Harley decided was probably a good way to go. It's a cross helical structure. So from the side, you can see these two alpha helices. And you can make this an arbitrary length. So from one, it's a repeat protein. So every one of these cross helical bundles is identical. And you can make this, we've made them from 4 repeats to 34 repeats. Now, along the alpha helix, you can put in different amino acids. We're using glutamates, which presents carboxyl groups. And we can arrange the carboxyl groups to match any array of cations. So the idea is to match the array of carboxyls to, say, the cation sites on a mineral surface. In this case, this is one that Fatima designed to bind to the O12 face of iron oxide in the form of hematite. And it turns out when you put it down and look at it with AFM, they're all aligned on the O12 face in a certain orientation. So that works. All right, so we first asked the question, well, are we really making something that works the way we think it does? And so this is work that's been published now for a number of years, and where Charlie worked with my former postdoc, Shui Zhang, who's now a research faculty at University of Washington. And we chose mica because it's an atomically flat surface. We know how to interrogate. We know the structure. So we designed it so that carboxyl groups match the hexagonal array of cation sites on the mica surface. And we looked at a number of different lengths. And so we expect that these things will bind along 3 directions on the mica lattice. Here's the AFM image of the mica lattice, and here's the protein on top. And indeed, you can find proteins lying in all 3 directions. But it's not that simple. It turns out that what we get depends on what the solution composition is, what electrolytes are in the solution. So at a low concentration of potassium, we find that we just have proteins bound to the surface. These are in situ AFM movies. These are actually high-speed movies. They're a frame a second, which is from someone who started AFM 30 years ago when it was like 5 minutes a frame or something like this. And we could only save 4 images before we had to write them to a floppy disk. We now collect 1,000 images at a frame a second. So these are the individual proteins. These are mica 18 repeats. And one thing you'll note immediately is that while all 3 directions are present, one dominates. And we'll come back to that. That's a really important observation. All right, if we go up in salt concentration, now all of a sudden things look much more dynamic, and that's why the image is messy, because the proteins are moving. And this takes a while to play because it's a lot of data, so I'll speed it up. And you can see what we end up with in this case. We end up with this, what's called a high-density disordered phase. That's the terminology for this in a threefold potential. You call this a high-density disordered phase, and this is just a larger scale image showing you what the end state is. Little domains that lie along one of the 3 directions. If we go to even higher salt concentration, we see something quite different, and you'd say, well, what are we looking at? It's a 2-dimensional liquid. So they're so mobile now that they're essentially a nanorod liquid in 2D. The bright yellow is actually protein stuck on top of the liquid. We don't know if these are mutant proteins, and so there are a few of them stick. We don't know why, but there's a few of them. But here's what happens. So if you watch carefully as this goes on, you'll start to see domains appearing. But you'll notice that these domains only start appearing along one direction. They never show the other 2 directions. And the end state of this surface is really quite remarkable. It's a 2-dimensional smectic crystal with 1 billion proteins all co-aligned in rows. Now, I'll mention that there is no smectic phase in 2 dimensions, right? In theory, there should not be a smectic phase where they lie in rows. A nematic phase where they're all co-aligned but are random along the length of the rods is what would be predicted because the thermal energy is too large for the binding energy within a 2D smectic phase. But of course, these are interacting with the substrate through very specific interactions, so we're stabilizing something that wouldn't exist in 3D. All right, so none of this is in the design, right? We didn't put this in the design. If we now introduce an interaction at the ends of the protein, so the ones I just showed you can't bind to one another at the ends, but if we allow them to bind, even in a hydrophobic interaction, we now get single protein-wide nanowires that cover the entire surface. And if we build in a threefold interaction at one end and leave the twofold interaction at the other, they self-assemble into a hexagonal network, co-align with the mica lattice, where the pore size is defined by how many repeats we put in the protein. Truly a remarkable outcome, okay? And not in the design, right? I mean, we didn't set out for, well, this actually, I should not say that. Now we've built in interactions that drives this design. That's not a fair statement. Okay, so the basic design works, but the assembly outcomes reveal the importance of effect from solvents, ions, and substrates. I showed you the effect of ionic strength already. That gives us quite a different outcome. If we look at the nanorod length, I showed you we can go to the smectic phase. This is actually a 14, not an 18. But if we go down to n equals 6, you see nothing. It's not because there's no protein on the surface. It's because it never gets out of the liquid state. If we now go to look at different ion types, rubidium does the same thing as potassium, but sodium at the same concentration again leaves it stuck in the liquid state. Now here's perhaps the most remarkable outcome. This is what we get on muscovite, which is one type of mica. You get the smectic phase or pneumatic phase if it's not quite as high a concentration of salt. Fluoroflogopite is another type of mica that has exactly the same surface lattice. That lattice I showed you in an early slide, it's the same in both cases, but we can never get out of the high density disordered phase. This phase will never appear, no matter how high the concentration of protein or salt. Why? So if we look at Monte Carlo simulations, this is where Monte Carlo simulations done by Orion Dollar, who's a student of Jim Fentner's, our collaborator at University of Washington, and working with Chris Mundy, my collaborator at PNNL. What you will find is that if you have reversible binding to a surface, but you don't allow translation or rotation, you can never leave the high density disordered phase. You will always see this phase at high protein coverage in a threefold potential, right? Because there's all three directions. And you can see why that is, because a little domain nucleating over here doesn't know about this one over here, and so they form independently and they all get stuck. It's a kinetic trap. It's not the equilibrium state. If you allow them to be able to translate and rotate, you will, I guess I need to play them. Well, that's weird. I don't know what's going on. This is supposed to be a movie that plays. Maybe I just forgot to, no? Huh. What happens is, unfortunately I can't show you. In this case, it starts out like this, but the red domain takes over, and you end up with all co-aligned, because that's the lowest energy state. Entropy determines that. But these two can't be, you can't have both cases, right? It's either one or the other. Either they have mobility or they don't. So how is it that we can get a difference between fluoroflogopite and mica, where fluoroflogopite is apparently here and mica is apparently here at high salt concentration, but between fluoroflogopite and muscovite, they're both mica. But if we go from high salt to low salt on muscovite, we go from here to here. And the answer turns out to be incredibly surprising and important. What is the difference between fluoroflogopite and muscovite? So there's the mica structure. It's a layered compound. Here's the layer that we're interacting with. But below that layer are these OH groups. And you see they point in a certain direction. And if I look down on the surface, you see the blue, the green, the red, and the pink. Those are OH groups in 4 successive layers. Now, they only point in one of 2 directions. This direction or that direction. So that layer's like that, the next layer's like that, the next layer's like that, the next layer's like that, and never do they point along that direction. So of the 3 equivalent directions in the surface lattice, the hexagonal lattice, one of them doesn't have OH groups pointing along it down below the layer. That's a unique direction, and that's the direction in which all those domains form when I showed you that 3 molar salt concentration where you get the smectic phase. Well, here's the surprise. It's all about the water. So what the molecular dynamics shows us is that if we look at fluoroflogopite, I should say, so that's muscovite mica. In fluorofluorocapite, the OH is replaced by fluorine. So this directionality is completely removed. And now when you look at the water structure above the surface, even though these OH groups are down below the surface, what you see is on muscovite mica, you have a hexagonal pattern in the first water layer, and the waters point in all three directions. And the second layer is still hexagonal, and then you can't even see the structure by the time you get to the third layer. But on muscovite mica, even though you have a hexagonal pattern of water, it's unidirectional. And that drives the second layer to form stripes. You're looking at water density here, okay? And so the threefold symmetry is broken. Now, that explained, and what's beautiful is what Elias Nkusi showed is if we use our fast force mapping that Calvin showed in an early slide with this water structure, we can see this striping. We have a hexagonal first layer, and we see the striping in the second layer above muscovite mica. We haven't done the experiment on fluorofluorocapite yet, but, so hopefully we won't see the striping on fluorofluorocapite. And of course, as we change the salt concentration, we're changing the height at which the proteins interact with the mica surface. And so our conclusion is that the difference between the fluorofluorocapite and muscovite is one of them only has a hexagonal pattern of water, the other has both hexagonal and a twofold. And as we increase the salt, we drive the proteins away from the surface, and they're interacting with the twofold pattern of water, and that drives them to this twofold structure. All right, so the last thing I want to tell you about is our use of these designs in order to try and direct the formation of crystals. That's what we wanted to do to begin with. We only did the mica thing to see if we could successfully design proteins that interacted the way we wanted them to. And here we took a little more of an agnostic viewpoint. We said, well, we can make lots of these kinds of proteins, and there are lots of different faces and phases of calcium carbonate, so why don't we do the experiment and see what phase forms and what face it forms on, and then we'll learn from that what the design rules are. And so we did a number of proteins, and we also took a random charged protein, bovine serum albumin, as a control. So if you now crystallize calcium carbonate, this is work from Biao-Jin now, without protein, very typical pathway, you make amorphous calcium carbonate, it changes to vaterite, and eventually it's replaced by calcite. If you throw in BSA, the same pathway holds, but the time scale for these transformations is just extended. If you throw in one of these proteins, I'm only going to talk about one because otherwise we'd need another couple hours. So if you throw in DHR FD31, FD stands for Fatima de Villa. Okay, so it's number 31 of her designs. Okay, so what does it do? It forms nanocalcites directly, and they have 110 faces, which is not the equilibrium face of calcite. And these assemble then, eventually forming rhombohedral plates, but you can see they do it by adding particles together, and they have to heal away these 110 faces to end up making the 104 faces. So let's look a little more detail about how this takes place. Biggest surprise of all. It turns out that the first thing that happens is the FD31, the calcium, so there's no carbonate in the system now. The FD31 and the calcium assemble into these ordered supramolecular structures. And you can see this in the TEM data, in situ TEM data, showing the assembly of these things into these rectangular shaped structures. Okay, and so what do these rectangular shaped structures do? These are like ordered versions of what Asaf talked about with the polymer and the calcium yesterday. So here's this is kind of crazy. So now you introduce carbonate, and what happens? These things are sacrificial templates. Calcite nucleates next to them, but because it eats up the calcium, the templates fall apart. Now the proteins are released into solution, and now I guess the proteins stabilize the 110 faces, because otherwise we wouldn't have 110 calcite. All right, so that's pretty cool. The other thing to notice is that where the crystals form next to the template, it looks like they're not actually on the template. There's a little space that's just a little space, like a nanometer in size, that keeps them away, and maybe that has to do with the structured water region that I've been talking about. I don't know. So these particles are only 3.3 nanometers in size. I don't know if anybody's ever reported nanocalcite at 3 nanometers. I think it's unique. And then they assemble together. They make these 110 bound particles as they assemble, and eventually they're going to, well, I'll show you what happens eventually. So eventually you can see this is a really lousy crystal, but it's building these 104 bound crystals, and I think this is a movie of a pretty well-formed 104 with particles still attaching to it. All right, so that's the story. So where do we go from here? So I thought maybe I would, instead of sort of concluding by summarizing, I'd tell you what has to happen in the future. So the first one is, we don't really understand well how surface chemistry and symmetry elements of substrates and proteins are imprinted on the overlying solvent and ions, but it's clear that's a very important aspect of the interaction and the outcomes. Secondly, we don't understand how the solution structure alters thermodynamic properties or how they evolve as surfaces approach one another and begin to interact. But it's clear that they do change thermodynamic properties. And then the third one is really sort of a technological in the sense that we have to build up the capability computationally, I suppose. We have to learn how to account for a combination of all these interactions, the epitaxial relationships, the solution structuring, and the entropic factors that drive, say, liquid crystal formation or the supramolecular assembly, if we're going to accurately predict the mineral templating by protein scaffolds. And with that, I tried to acknowledge the people who did all the heavy lifting, in particular Susrit and Sam in the case of the Emelogen and nanoribbons. Jejun did all the high-resolution imaging of those. The mica and assembly work, Shui and Harley I mentioned. Rob and Jesse and Orion, well, Rob and Jesse did the modeling of the water structure, and John and Orion did the Monte Carlo. And then the calcium carbonate protein templates, that work I mentioned, the people who did the heavy lifting there. And this work is funded mostly by DOE's Basic Energy Sciences through our Center for the Science of Synthesis Across Scales. But the work on enamel is obviously not that, and that's funded by NIH. And I thank you for your attention.
Thank you, Jim, for the enlightening lecture. Now we open for questions. Okay, we have one there. Yeah. Okay.
Thank you, Jim, for the wonderful results. I have a question on this one that you show, the mica and the fluorinated one that had the same lattice constant, but the organization of water is different. So I was wondering if that's due to any polarization effect on the surface due to the...
Polarization effect?
Yes.
Yeah, that's a good question. So I don't know. I have to ask Rob. How does that come down to polarization? I mean, I guess it must, right? What else can it be? Like, there's an OH group there. It must be the dipole moment of the OH, right?
Yeah. Okay. Yeah. And the other questions, you show the images with the structure of water. How did you get those images with the, which technique is that?
Yeah. So fast force mapping, what you do is you oscillate the cantilever up and down, and as you come near the surface, because the water density is varying, well, that assumes the only interaction is with the water, but the truth is that in a lot of systems, the interaction is also with, say, OH groups in the lattice, so you have to be careful. But nominally, if the water density is varying, then what you're going to see is a shift in amplitude and a shift in the phase. You can directly relate the phase shift to the density difference in water. And if you have a very sharp tip, you can get atomic scale mapping of water structure. It's truly phenomenal.
That's amazing.
Yeah.
Thank you.
Thank you, Jim. It was a fantastic presentation, amazing work.
Thanks.
Wow. Maybe I missed in your first system where you had the nucleation kinetics with different proteins of your, was it calcium phosphate?
Calcium phosphate, yeah.
All right.
Yeah.
I was wondering, forgive me because I don't work with proteins, but whether the proteins will impact the pH of the crystallization media at all, and if that could have an effect on and whether you control the pH in the case.
Not in our case, because we're flowing solution of fixed. I mean, maybe there's, if you want to talk about local pH, yeah, I mean, definitely, surfaces, because protons will come down or OHs will come down. That may well be going on there. I won't, I would throw that into the term of interfacial energy, right? I don't know what else to do with it. Yeah.
Okay, we'll take the last question. Yeah.
Again, fascinating, and maybe mainly the kinetics. But I want to ask on something very small. You showed this alignment of the proteins. Is it the direction dictated by something external, or it's a collective decision that
It's a
can
collective
go
decision.
on arbitrary direction?
No, it's not arbitrary. It's only along, we determine this. We determine the orientation of our mica. It's along the 001, or the 100 direction on the 001 face.
Substrate.
It's the unique direction. So the OHs point along these directions, and the domains, when they're
before
ordered.
the mica, I think it was a liquid phase that you showed.
That's on mica.
On mica.
It's on mica.
Substrate
And the orientation of those domains
Okay,
is
thanks.
that alignment right
Clear,
there.
clear.
Yeah, yeah. Which is the direction of the striping of the water.
Great. I encourage you to have a chat with Jim if you have more questions. I'm sure there are many more. Our next speaker is, yeah. Thanks again for the. Next speaker is Tomchev Ranchevsky from Southern Methodist University. He'll be telling us about the story in Tahiti.
I guess I can use this one. But now the slides are off. Check. No, the slides are off.
Did you want to try the scan? Or does it's not in that direction.
Okay, a little bit of technical difficulties, but got it working. Whichever you want. Yeah, perfect. Perfect. So we couldn't start one presentation, and now we started two from all of a sudden. But it doesn't matter. Okay, I should hurry up because I lost a couple of minutes. All right, so the session today is crystals in nature and medicine. It's absolutely no debate that crystals in medicine are incredibly important, but today I will focus on crystals in nature. And if you ask why, well, you can look through the window, and it's beautiful. This is the Oak Ridge Lake, and look at the nature. How can we not look at nature and crystals in nature? However, I have to say that as humans, we are a little bit egocentric. Nature is just what we see around us, and that's wrong. Nature is everything. Nature doesn't see humans. And I want to make a parallel between the Oak Ridge Lake and the Ochridus lacus on Titan. Why should we look in our nature? Why shouldn't we look in the nature of space? And my talk today will be Titan in a jar. So basically the nature of Titan. Well, first, the outline of the talk. Why Titan? Then I will go with just one case study. I don't have that much time. The broader picture. Then I will talk about, from Titan to Earth. I will describe this a little bit later, and conclusions. Without further ado, why Titan? Well, we know a lot about Titan because Cassini-Huygens concluded in just a couple of years. It revealed a lot about Saturn and its moons, and that information was so interesting and intriguing that NASA decided to send another mission right away, which is a Dragonfly mission. It will take off in just a couple of years, and it will arrive in Titan in around 1 decade, around the time that I hope to be at the peak of my career. But unlike Cassini-Huygens, Dragonfly will stay on Titan for around 3 months, and it will explore the surface. The official, quote, unofficial, this decision why Titan is because NASA will be looking for life, right? Not life we know it, maybe past life, maybe current life, maybe future life, life nonetheless. So why Titan? Titan is the only other place in our solar system that has dense atmosphere. The atmosphere is made of, I can move on, it's made of nitrogen and methane. But in the stratosphere, we do have a lot of energy from the sun and Saturn's magnetosphere and a lot of chemical reactions. So we have production of a lot of organic chemicals, pretty much everything you can imagine having carbon, nitrogen, and hydrogen. So we have ethane, methane, propane, and many other chemicals of different complexity and structural and compositional. Now, if we take a look on the conditions on Titan, on the surface, of course, we have 93 Kelvin and around 1.5 atmosphere. Under these conditions, every organic chemist knows that only methane, ethane, and propane are liquid or gas. Everything else will be solid. So now think about it. Benzene, for us, just a simple chemical. We all have it in a lab. Just a solvent, but for Titan is a mineral, because by definition, it's a naturally occurring crystal on the surface. It is as mineral as it gets. So we call this organic, minerals on Titan or titanium minerals. If you want to learn a little bit more about them, about their complexity, with colleagues from NASA, we just published accounts of chemical research, just summarizing their structures. Now, I will digress, and I'm sure you would love this digression. The moon was the big deal of the past. The landing of the moon, the quite big of an event. Mars is present. Everyone talks about, the Curiosity rover, how cool that is, and so on. But Titan is the future. And look, the moon and Mars, with no offense and with all due respect, the surface is boring. I mean, the common minerals we have is just rocks. Titan is organic laboratory on a planetary scale, and now is the time for organic solid-state chemists to shine, and I cannot be at a more right place than this conference to just say, hey, this is our moment. We have around a decade until Dragonfly arrives, and we should grab this moment. My group just started working on this, but everyone is welcomed. Titan is a world. It's not just one single project. Okay, so I will now present one case study, because it's one thing to just dream about how we can explore space from the lab, in the middle of Texas, but it's another thing to really show results. And I decided to talk about acetylnitrile and benzene. The reason why is because both of them are the most common solvents by all metrics, and for me it's quite remarkable to discover something new about chemicals that everyone uses. And they are the most fundamental organic molecules you can find, one of the most, and the simplest. So solid benzene has been identified on Titan and confirmed on the structure. Solid acetylnitrile is only tentatively identified. The way how people would do this is we'll compare the spectral signature collected in situ from the moon, and then they will compare the spectral signatures with the database we have. Now this has been done for benzene, works like a charm. For acetylnitrile, not that much. There is a shift. And they concluded that, well, it may or may not be on the surface. But that is planetary researcher thinking, and that's wrong. As an organic chemist, the first thing that comes to mind, well, wait a minute, acetylnitrile and benzene, why would they occur as molecular crystals? They can be hydrates, they can be co-crystals, they can be different polymorphs, and I don't need to continue here, you all know the drill. And so we decided to look at the possibilities of acetylnitrile to exist in something else than a molecular crystal. Now, in the past, people would go and try to make a co-crystal, try to make a salt, and so on, which is okay. However, we decided to be a little bit more thorough than that, and we went with a phase diagram. When I say phase diagrams, people are saying, well, that's boring, that's science of the past. That's wrong. The phase diagram is the most fundamental descriptor of the thermodynamical equilibria of a mixture. And for me, it's quite surprising that no one talks about phase diagrams today. So we decided to go and recreate it. Another big surprise. The phase diagram of acetylnitrile is not known. It's the 21st century, and we don't know the phase diagram of a binary mixture that we all use. Sure, there are some descriptions from the 1930s, but hey, back then, the DSC didn't even exist. So we decided to, go back and recreate this phase diagram based on differential scanning calorimetry as a, very suitable method to do so. We can look at the crystallization, and we can look at the melting. Crystallization is arguably not a good idea because it's a kinetically driven phenomenon. Melting is more thermodynamic. So here I present the melting curves. If we take these melting curves, then if we look at the minima, and if we plot them, then we get a phase diagram. Immediately, it becomes clear that this phase diagram is not as simple as a single eutectic and just a mixture. This phase diagram is very rich. That tells us that there is a lot going on in this binary mixture. However, we don't know what. Sure, we have the shape of the phase diagram and the equilibria, but we don't really know those equilibria. If we want to learn about them, we do need to look at this isoplets with a structural method and, to discover what is inside this phase region. We can choose different methods. We can choose spectroscopy, we can choose diffraction, and so on. Arguably, the best method for this is powder X-ray diffraction. For a couple of reasons, and I can talk about this forever. Well, later we can talk if you want, but I will just mention that it's qualitative, quantitative. The sample preparation is extremely easy, and we can make it in situ and in the operando. I will here, and of course, we did collect for this particular case, I think it was 3,000 diffraction patterns, and I can do it in our lab, but if we do it in our lab, it will take us around 6 years, and I'm on my 10-year track, so I need to, move on. And that's why we moved to the APS, where we can collect it in just a couple of hours. I will here present just one of these isoplets, just so, to bring the point, but everything is the same for all of the remaining isoplets. First of all, we see exactly the same information that we see in the phase diagram derived from DSC. At the top of it, in the diffraction patterns, we can see no scattering, which makes sense, because on the top of the phase diagram, we have liquid. Then in the first region, the triangular one, we have scattering from one phase, and the rest is liquid, doesn't scatter. And down there, in that rectangular shape, we have two phases. This is already quite of an information. However, it's still not complete. What we do in our group for so long time, we do very detailed analysis of powder diffraction patterns, not just lamellar poly, but complete Rietveld analysis. For the first one, it's very easy. Rietveld analysis show that it's pure benzene. So in that region, we have solid benzene and we have liquid acetonitrile. However, down there, we see that we have additional phase, and that additional phase was unknown. That was another big surprise for us, how we can see something unknown for benzene and acetonitrile. Everyone is using them, you know. I was very proud of this. But we didn't know the structure. Solving crystal structures from powder is extremely challenging, as you might know. Solving crystal structures from powder, from a mixture with a preferred orientation, collected at low temperature is a little bit more complicated. But it's important, and it's fun, and we did it. And in this case, we can see how very interesting chemistry. We see that up there, we have a solid benzene and liquid acetonitrile. And acetonitrile, below the peritectic line, it penetrates the crystal structure of benzene and adopts a channel structure in which we have acetonitrile within the channels of benzene. This is a very, very typical peritectic phase transition. Now, this co-crystal is, would be stable on Titan. Now we'll just go back with the phase diagram. This phase diagram, as you can see, provided us with so many information about, the phase equilibrium. We can see how many phases we have, the phase lines, we can see the equilibrium and so on. But the picture was not complete. If we combine this with powder diffraction, now we have everything we need to know for this phase diagram. This is the complete picture of the acetonitrile benzene phase diagram. Now I will make just a couple of comments how we can use this for Titan. Absolutely, the first logical experiment to be done here is to see whether the spectroscopic signature of the co-crystal will match the spectra collected on Titan. We're working on that, and hopefully we'll be one of the few groups from Earth to have detected mineral in space. But here, because I don't have that much time, I will skip that and I will go and talk about something else. With a little bit of creativity, we can use crystals in a very unpredictable manner. We can use them as, for looking back in the past. Now, the lakes of Titan evaporate and then precipitate again. So that's a very dynamic environment. We do know that there are regions in Titan that they used to have lakes, so they're lake beds. The lakes are made of ethane. Ethane and acetonitrile are quite similar in shape and size. So our hypothesis was that if acetonitrile, we have a co-crystal with benzene, it can interact with ethane, and we can have a ternary, or we can have some sort of reaction between those two molecules. So we did an experiment in which we mimicked raining down ethane on top of our co-crystal, and then we did another experiment in which we soaked the co-crystal, and then we did another experiment in which we created this co-crystal in liquid ethane just to see how it will react, and then dry the lake. We see that we have splitting of the diffraction peaks as expected if we introduce ethane. We haven't solved this crystal structure. We are working on it, but even without solution of this co-crystal, think about it. We can use this to see if there was a lake at certain point in a certain space in Titan, at certain point in the 5.5 billion years that Titan exists. Of course, that's not the proof. However, I do think that it's very interesting to use co-crystals as something that can allow us to look in the past. Okay, so if you want to learn about this particular topic, this particular system, we publish it, and also the reference of the accounts, paper is out down there. But for the rest of my talk, I just want to say that this is we need to look at the bigger picture. I just presented one example. Currently, we are writing papers on 4 more that are binary mixtures. We started working on ternary mixtures, because Titan, it's not a well-defined environment in which we can just say, oh, there's just benzene and acetonitrile. Titan is a mixture on a world scale, but we need to start from somewhere, and we need to start building those models step by step. Another part of this broader picture that I want to talk about is structure. So far, I spoke about crystal structure, and we do that quite professionally in our lab, but a lot of chemists, structural chemists, are very blind to other structures. Structure is an umbrella term, so we do need to look at it from different aspects, especially if we look at worlds, not at one single system. As I said, it's an umbrella term. In my lab, we do not cover everything that falls in that umbrella, but we do quite a bit, and I just want to very briefly talk about it. First, we look at local structure. We use pair distribution function. A local structure can give us a lot of information about amorphous structures, about crystal growth, and about defects within the crystals. Then, of course, we look at vibrational structure for two reasons. First is sensing, but then we also look for vibrational structure to compare it with our crystalline structure. Now, we use Raman because it's a great method. We have it in the lab, and it's amazing. However, if we really want to learn about vibrational structure, Raman is not the way to go. Vibrational neutron spectroscopy is the way to go. And I can, again, talk about this for ages. Long story short, Raman is amazing, but with Raman you have interaction between photons and electrons, and that, as the theoretically speaking, it's incredibly difficult to model. In vibrational neutron, it's as simple as it gets. We have neutron and we have the nucleus, particle-particle interaction. We can get so much more information. Then we also look at the dynamics. Many people in the audience will appreciate dynamics. Crystal structure is static. When we see the crystal structure, people think that everything is frozen in space. It's not. And I'm not talking only about rotors. I'm talking about everyday normal structures. For example, here for propionitrile, we use quints. We see that we have dynamics, even though propionitrile is not a rotor. We use inelastic Newton scattering. Of course, solid-state NMR is another method. We don't do it in our lab, but I do think that there is very complementary because it accesses a completely different time scales. We also work in a direction of thermal expansion and macroscopic crystal growth that's very important for origins of life and for the scattering, overall scattering on the structure of Titan and on the surface of Titan. As a conclusion, I will keep it short, and I will say Titan is a world. This is only one example. I can present many more examples with completely different takes, but this is a world, and it needs to be explored a little bit more thoroughly. And there were a couple of articles written about this idea of exploring worlds in the lab. And recently, we gave an interview with a couple of other people in the New York Times, but also at Wired and The Economist. So if you're lazy to read articles, those newspapers are so much easier to read. Now, before I conclude, I just want to say that when I started doing this, a lot of people would say, this is okay, this is great, but this is not applicable. You're looking at some models in a far world place, so why should we care? Even back then, Dragonfly wasn't announced. So Dragonfly got announced a little bit later after we started working on Titan. And then, back then, I thought that, well, if you're a little bit creative, you can use this knowledge in many different directions. Back then we couldn't prove this, but now we can, and I will just use 1 minute to talk about it. Having this knowledge on Titan can inform a lot of research that can be done in the lab with applications in our world. So let's go back from Titan to Earth. We have 3 offsprings from this research, which are 100% Earth-based. One of them, well, 2. One of them is high-pressure synthesis of extended solids and thermal expansion elements. Look, benzene, if it's put under pressure, goes in graphene. But what about the co-crystal between benzene and acetonitrile? What will happen if we put it under pressure? It will get to a completely new material. So we can really synthesize extended solids with the new structures and new compositions. Another project that we just started is copying this framework to organic minerals on Earth. There are a lot of organic minerals on Earth. We do not know their structure. We do not know their phase diagrams. We need to solve that if we want to understand Earth, as well. And then finally, we just got funded for this. We have a really interesting idea of mimicking life on Titan, and I hope that in next ICOS I can provide a little bit more information about this. Acknowledgements, well, my group is very small, and our focus is actually pharmaceutical crystals. It's not Titan, but we do try to, work on some interesting cases which are more for fun. This is a passion project. This is not anything else. And we have a lot of collaborators in general, not just for this, but for our other projects. And funding, quite important. Acknowledge to that. And thank you very much for your attention.
Thank you, Tom Chair, for a nice detective science story. Yeah, a few questions here. Yeah.
Thank you for the Titanic talk.
Thank you so much. I'll appreciate the fun.
Your phase diagrams, are you considering pressure as well?
So we do for our material design, not that much for Titan. For Titan, we are so lucky. The pressure of 1.5 atmosphere, exactly similar to Earth, and the temperature is slightly above liquid nitrogen. We are as lucky as it gets.
Hi, it's very interesting research. What I want to know is, other than temperature and pressure, the presence of surrounding so many other chemicals may also influence how a crystal structure of benzene or acetonitrile is in Titan. So in your lab, maybe you can kind of imitate a few factors, but how do you really make sure what you get will be similar to what is there in Titan?
There is everything on Titan, but we need to start from somewhere. And the first step is the binary mixture. Second step, ternary mixture, and so on. We need to start from somewhere. And the complexity will grow, of course, but better to know something than nothing.
I'm Consiglia Tedesco from the University of Salerno. I would like to ask you some details about the structures of acetonitrile molecule inside the channels.
So the crystal structure that we solved is from powder, and there was a lot of preferred orientation. There was a lot of another mixtures and so on. So we are very conservative in what we can learn about it. So we are short on bond distances and lengths, but we cannot really talk about electron distribution and so on. So to really look at changes in the molecule of acetonitrile.
So I was just wondering if you use the model and if you just considered the CH-pi interactions between acetonitrile molecule.
Of course there are interactions, and we hope to leverage those interactions in creating extended solids. Whenever there are pi-pi interaction, there is a potential for forming a new covalent bond.
Yeah, I have two more questions. Yeah.
Great talk. So most of the molecules that you've shown in the first slide, or first couple of slides, were either hydrocarbons or had nitrogen. Is there oxygen on Titan?
The oxygen there is as water because it's an icy moon. However, water is not in the atmosphere. Now, the water is only on the surface. We do include water, but it's a little bit more complicated than that because it doesn't take part in that atmospheric chemistry. However, that's a great point. There is oxygen from the water, but not as much as nitrogen and carbon.
Does that water hydrolyze any of the nitrogen?
That's a great point again. The only way how water can get into this chemistry is by impact, for example, from comet or something, or asteroids, that we have a huge release of energy on the surface, because we cannot really think of any other way of how we can get water from ice to our molecules to do some sort of chemistry. But that's an excellent point.
Thank you.
Microphone, yeah.
Hi there. Tomislav Stolar from Ruđer Bošković Institute in Croatia. So thank you for this fascinating talk on extraterrestrial co-crystals. I'm wondering, do we know something more about geological and environmental conditions on Titan? For example, are there any tectonics, earthquakes, impactors?
So we do know, and actually in our lab we have another case, I didn't have the time to talk about it, which is more recent. We use thermal expansion to really mimic and see how the karstic landscapes could form on Titan. There are karsts on Titan, for example. So we can use co-crystals and we can use molecular crystals to really recreate also the geological titanological feature on Titan. And there are earthquakes on Titan, but I would say that we should call them Titan quakes, not earthquakes, just to be very on point.
Thanks.
Thank you. Yeah. Okay, so we'll have our next speaker. Our next speaker is Jared Coquero from University of Rouen, France.
Okay?
Yes, that's good to go. Thank you.
Okay, so good morning. This is already afternoon, I suppose. Oh, okay, so good afternoon, everyone. Thank you, Panche, and thank you for the organizing committee to invite me to present this lecture on the transfer of chirality. So I will right away depict the outline of my talk. There is a pointer. Okay. So first, I want to clarify what is supramolecular chirality and intrinsic chirality, and then I would like also to express the, I don't know if you know that, about the racemization process and preferential crystallization. So it means access to single chirality by two different means, but always by using crystallization. And then I will present the target molecules and what we have done with that and the transfer of chirality itself, and then we will try to draw some conclusion. Okay, so intrinsic chirality means that your molecules, well, first chirality, probably you know, it means that you have two molecules which are mirror-related and not superimposable. And intrinsic chirality, usually we don't use this adjective before because it's supposed to be always like that. So you have here a stereogenic center. Here it's a carbon which has 4 different legs, and then it makes this molecule different from the other one, which is mirror imaged. So these types of symmetry is very important for living organism, and life has also a marker of homochirality. On top of that, if you develop some drugs, you could have a good effect for one enantiomer and a counter effect or very dreadful effect for the other one. So separation of the enantiomer is a real issue in pharmaceutical industry. Here is also for fragrant industries, there are also some problem with cis trans or also chirality. So what is supramolecular chirality now? Let's take this stick, which is composed of prism, and you can see by the top of one over there, you can see that actually they can be bent because they can rotate one onto the other. So starting from that linear assembly, you can progressively turn on the left-hand side, so counterclockwise, and then you can obtain this assembly, which is clearly chiral, so it's coiled around the vertical axis, and then you can do the same but the opposite way, clockwise. And these two objects are composed of units which are not chiral, but the whole object is chiral, okay? And we call that supramolecular chirality. Example of that is quartz, alpha quartz, beta quartz. SiO2 is not chiral in itself, so when you have a liquid, you don't have any chirality. But if you crystallize them, and then you obtain for the alpha quartz, P3 1-to-1 or P3 2-to-1 for the other enantiomer, which means that you have built macromolecular assembly, which are themselves chiral. So now we can use that to obtain homochiral crystals. So how does that work? With intrinsic chiral molecule, we will suppose that we have what we call in our jargon conglomerate, which means that every enantiomer crystallizes in its own. But we will, in addition to that, suppose that we have also a fast racemization in the liquid state, which means that the two enantiomers can interconvert chemically. Okay, so that could be done by thermal activation, but it could be done also by catalyst, sometimes by protein. And if you have these two conditions fulfilled at the same time, then by applying an energy input in your system, which is very simple, it could be simply continuous grinding, okay, or it could be just temperature cycling. You increase temperature by 10 degrees and then you decrease slowly and you repeat that cycle. Or you can add ultrasounds also, and then you will have an irreversible evolution of your system towards homochirality in the solid state and always a racemic mixture in the solution or the molten state. So this is a very important discovery because this could explain maybe the spontaneous evolution towards homochirality, so the first step towards life. If now you have a supramolecular chiral crystal, what does it mean? It means that you have this situation here. But you don't have to care about what is happening in the liquid because here you don't have any chirality in the liquid phase. So you can apply the same process, okay? And this was actually obtained for the first time by Viedma by using sodium chlorate, which of course has no chirality in the liquid phase. So now, thanks to the previous speaker, I can show some phase diagram. Okay, that's very nice. But here, the phase diagram will be very special. Why? Because you cannot access to anything, to anywhere else in your phase diagram that's the racemic plane which is there when you have solution. Because the solution needs to be absolutely racemic. Okay, so the only thing that you have is the intersection of that racemic plane with the saturated double solution which is there. And then you start by a system which has one enantiomer and another enantiomer here, and with this racemic plane. And by applying this flux of energy in the suspension, you will have this irreversible evolution towards one enantiomer or towards the other. And this is stochastic if you don't have any impurity, chiral impurity inside. Now, if your molecule cannot interconvert, so they are definitely right-handed molecule and left-handed molecule and then cannot interconvert, there is no RS equilibrium. If you have this chiral discrimination in the solid state, starting from a supersaturated solution by seeding with a single enantiomer, you can start crystallizing this enantiomer that you have seeded. Okay, and then you have secondary nucleation, and then you have a clear crystallization which is stereoselective, which is then preferential. And then you can collect the crystal before the other enantiomers start to crystallize. And by recycling the mother liquor that you have here with an excess of S, you can then after crystallize S, and then R again, and S, and then etc. And this process could be used at industrial scale, and it works perfectly well. So the molecule I will talk about now is a target molecule, is this one. And it has been already published as a conglomerate forming system. So we were interested in having both enantiomer of this molecule. First, as it is a conglomerate, and this was published then, we tried to attempt racemization, because if we have racemization and this conglomerate, so we have the two conditions fulfilled, and then we could deracemize. But unfortunately, by using UV and at different wavelengths, different energy, and so on, we got much more chemical degradation than racemization. So we could not use that. So I will depict how we performed the preferential crystallization. First, let's go back to the synthesis of this molecule. So it's pretty easy with two steps. So starting from the thiol here, we condense with the chlorine derivative here. So this alkylation is within good yield, and we obtain the sulfide that you can see here. And the sulfide needs to be oxidized softly to obtain the sulfoxides. Okay, so the R and S sulfoxide, only you know, a racemic picture is presented here. But unfortunately, if you, by all the different oxidation agents that we use, we got a mixture actually of sulfide, sulfone, and the 2-sulfoxide. So we have tuned a little bit the condition so that we got mainly sulfoxide and still sulfide, but with no sulfone. Why no sulfone? Because sulfone can make a complete solid solution with the chiral molecules here. Okay, so the impurity, which has not any intrinsic chirality, can adapt to both enantiomers, to both crystal lattices of the two enantiomers. So we checked that by using X-ray powder diffraction, that we have a complete solid solution. And indeed, if we concentrate on the two peaks which are spotted here, we can see that we have a continuous evolution of the parameters, and indeed we have a complete solid solution. So this is why we adapt the synthesis so that we don't have this sulfone inside the crystal lattice. And then when we look at the complete crystal structure, we were then not surprised to see that the same space group, very similar parameters, and then if you look at the volume of the unit cell, it's almost the same, which confirms that the lone pair of a sulfur atom is almost as bulky as an oxygen. And look at the projection of the crystal structure, you can see that they are almost the same. Okay, so as there is no deracemization with the sulfoxide, we said, okay, but with the sulfone, we will be able to deracemize, because here there is, of course, no intrinsic chirality, so we have only the two possibility of crystal packing. And then we implemented the Wiedemann ripening on the sulfone, as it was difficult to monitor because it's only chirality in the solid state, and at that time I didn't have a VCD in my lab. So we decided to do it for 1 week. For 1 week, so we use crystal beads that you can see here and the magnetic bar. So we were constantly grinding the crystals, and then you have this irreversible evolution towards one of the two enantiomers. And then we collected these seeds, these crystals, as seed for the preferential crystallization, okay? And we repeated this experiment several times to have a collection of different possible enantiomers, okay? And then we perform the preferential crystallization, which means what? We have here two isotherms, which are extracted from this figure here. So starting from the racemic composition, which is pointed here, we got at the high temperature, T2, and then we dissolve everything. Then we cool it down, this solution, to T1, where we have got first a supersaturated solution, and then we seeded this supersaturated solution with the sulfone, which has been deracemized. And then you can see what we obtain. Okay, so at 18 degrees, by letting 15 minutes, and by seeding with the sulfone, deracemized sulfone, we obtain S enantiomer with a quite good 91% of enantiomeric excess. Then starting from this solution, now we get an excess of R inside, and indeed, at the second run, we obtain the R enantiomer. So we had the clear evidence here that starting from a molecule which is not chiral, but crystallizing in a chiral space group, we can initiate a preferential crystallization on a chiral molecule. And we repeated this experiment with another run of deracemization of sulfone, and fortunately, we got the other enantiomer. I told you it's stochastic evolution. And then by seeding with this other crystal of deracemized sulfone, we obtain much better enantiomeric excess, 98%. And then we recycle this solution, and then 98 again. And then at the third run, we got 91, but with a good yield. So, the conclusion of that piece of work is that the sulfoxide and its corresponding sulfone can make a complete solid solution. Okay? And this could be used. Okay? So what I want to do now is to have a survey on the Cambridge Structural Database and to see all the different sulfone which crystallize in a chiral space group. Then, of course, that will be a pretty good indication that the corresponding sulfoxide could crystallize as also a conglomerate. And this is important because if you start from the discovery of Louis Pasteur in 1848, no progress has been made on prediction of conglomerate. 174 years later, no progress. Do you know many scientific problems which are still at the starting point and nothing improved? So second, the sulfoxide is not suitable for deracemization, okay, because it's not racemizable, we have chemical degradation. So the sulfone was first deracemized as a supramolecular homochiral seed, and we use them to induce preferential crystallization, and it worked. Okay? So we have now, on this example at least, a continuum between supramolecular chirality of the sulfone and the intrinsic chirality of the sulfoxide. So this work has been done by Marieh Al-Handawi, a PhD of mine, which was also, co-supervised by Dr. Ivo Rivelt. And on next October, we start a new PhD with a new student, and to see to what extent we can use this continuum, and do we need indeed a continuum? Maybe partial solid solution will be enough also to use this supramolecularity to induce specific chiral crystallization. Thank you for your attention.
Thank you, Jared, for a nice presentation about this chirality and chiral separation. And we open for questions. Okay.
I know very little on chirality, but I have something logically that I'm wondering about. As far as I know, if you have chiralic molecules, the crystal must be chiralic. Is that correct?
Yes, yes.
So when you say that you can create a chiralic crystal with non-chiralic molecules, my question is whether you have a hidden chirality that you don't see when you look at the ions, but maybe the molecular orbital, something hidden there that dictates chiralic crystallization. A question, I don't know.
Okay, thank you for the question. First, of course, if you have an intrinsic chiral molecule, the three-dimensional crystal will be also chiral. Okay, so that's intrinsic chirality imposes supramolecular chirality. But it imposes, but it is not a sufficient condition. You can have homochirality without any chiral units. It's the way these units are arranged in space that provide the supramolecular chirality.
But why? Why dictates chiralic crystallization?
If, for instance, you are interested in minerals, okay, and you will look at, you go in a shop, and you look at the hemihedral faces of quartz. And unfortunately, quartz does not show many hemihedral faces which will enable you to recognize if it is a left-handed or right-handed quartz crystal. But I can tell you that there are some samples in which, in a close vicinity, I mean, it's half a centimeter, you have one left-handed quartz crystal which has grown, and a right-handed quartz crystal which has grown close together, but differently. And sometimes this correlation is so close that you have what is called a twin. But in fact, it is an inversion twin, so, and this is not good to make piezoelectric materials, because then you have both in the same particles. I won't say the same crystal, because there are two crystals which are interdigited.
Okay.
I hope I've been clear. The jargon is a little bit special, so at first it's not that easy to enter in the kingdom of chirality, but it's really fascinating. Trust me.
It is, yeah. I encourage you to, we won't take any more questions, so this will be a good topic to continue discussing on the boat, actually. We have a boat trip at 12:40. The boat is waiting for us. So you can find each other to have a deeper discussion. Yeah, I will ask you to maybe hold a question. Maybe you can talk about the question on the boat, because the boat will leave at 12:40. We're short of time. So I want to ask the 5 speakers to come to the front. We can take pictures. And thank you all for the wonderful presentations. Please join me for another round of applause. Yeah.